A very good morning to all. Very good morning. Now we are going to enter into the 9th session of this short-time course. Today we have Dr. Saheli S. She is from NIT Silchar. Ma'am will be taking a session on the topic evaluation of reliability in power distribution system. So let me give a brief introduction about the speaker now. Saheli ma'am did her BTech in electrical engineering from NIT Agartala and MTech in power and energy systems from NIT Silchar. She has done his PhD from NIT Agartala. Presently, she is working as an assistant professor in the Department of Electrical Engineering, NIT Silchar. Prior to joining NIT Silchar, she has been an assistant professor in Department of Electrical Engineering, NIT Agartala. Her areas of interest include reliability of power system, distributed generation, microgrid operation and economics, and optimization. It's a pleasure to have you with us. Now, let me request the speaker, Dr. Saheli Ray, ma'am, to take over the session. Please, ma'am.
Thank you, sir. Thank you so much for the wonderful introduction. So, we'll be starting our session. Am I audible? Okay. So, we will be starting our session on evaluation of reliability in power distribution system. So, to start with, this is the presentation outline. Reliability, then power distribution systems reliability, that is, according to power distribution system, what does reliability mean when we apply to this? After that, we'll be discussing about the reliability parameters. Then there are some indices, reliability indices, which are based from the customer's perspective. Then we'll be having the study of effect of basic protection devices on the reliability indices. After that, effect of distributed generation on the reliability indices. After discussing all this, we'll just have a look at some of the works done by us in the allocation of switch and distributed generation. So, then, to start with, what is reliability? So, whenever the term reliability comes, we can understand that it's an inherent characteristics and a specific measure that describes the ability of a system to perform its intended function. If a system performs its function, which it is supposed to perform, then we call that the system is reliable. It may be applied to anything, irrespective of electrical engineering or any other field. Now, when it comes to power system, the intended function of a power system, the basic function is to provide uninterrupted power to its customer at an economic rate. So, reliability is measured in this perspective. How much able it is to fulfill this requirement of providing uninterrupted power to its customer at an economic rate. Now, why reliability is important? Actually, when it comes to the present day market, power market, the present day power distribution system is a deregulated one. Competitive market it is. So as because of the deregulation, several competition is there in the market. So customers are demanding more economic power, more reliable power. Because of the deregulation, because of the increase in the competition in the market, the demand has also increased about the quality of the power. As a result of that, the reliability perspective has become very important, especially in today's scenario. Along with it, we all know that today we are gradually moving towards a digital revolution. Most of the equipments that we use are digital devices. And these digital devices require uninterrupted electric power very much. As a result of that, this is also one of the reasons for why demand for uninterrupted electric power have increased manifold, especially in today's scenario. Now, to understand the importance of reliability, if we see this third point is actually focusing on that, and availability of 99%. If we say that a system is 99% reliable, then it might seem that for 99% of the time power is available. It might seem impressive, but that 1% of unavailability actually means that about 8 hours and 45 minutes power disruption in a year. And this whole disruption is also not considered satisfactory. Especially in the developed countries, the consumers will not accept this much of interruption, 8 hours and 45 minutes in a year. So from this we can understand, even if a system 99% availability is there, then also there is a huge scope of improving the reliability of the system. Now, again, to start with power system reliability, broadly it may be classified as generation reliability. We can analyze the generation system's reliability, then transmission system reliability, or a combination of generation and transmission system reliability, and distribution system reliability. Because we all know that the power system is broadly can be classified as generation, transmission, and distribution. In each of these phases, reliability evaluation may be done in its own way. In today's discussion, we will be specially focusing on the distribution system's reliability. Now, what is the importance of this distribution system reliability? Basically, if we compare distribution system reliability with that of generation and transmission systems reliability, we'll see that whatever research works have been done in the past few decades, most of the works concentrated mainly on the generation and transmission reliability. Though in last few years, in the last few decades, all the reliability works are also concentrated on distribution reliability, but still more work has been done on generation and transmission reliability, considering the fact that if any fault, any interaction occurs in the generation side or the transmission side, the effect will be catastrophic, right? Because it is connected to the whole system. The generation and transmission caters the whole system. But if we concentrate on the distribution reliability, since distribution system has local impacts, any fault in one distribution system will not have impact on the other side. It is a localized area. So comparatively, it may be considered that they will not have that much catastrophic effect as that in generation and transmission. But on the contrary, the irony is that it has been found that almost 80% of the outages, I mean, most of the outages causing interruption to the consumers or the customers, we can say, are caused due to distribution systems fault in the distribution system. Now, from there, we can understand, though distribution system has local effect, but since most of the faults are occurring due to these local effects, if we combine all these effects together, the overall effect of interruption towards the customers is mostly due to the distribution system's fault. So though it may seem to be comparatively less significant than the generation and transmission reliability, but actually distribution system reliability is to be focused most importantly, because as a customer we will bother about only that interruption. We will not think whether it is due to generation systems fault or transmission fault or distribution fault. We will just check, our matter of concern will be whether we are receiving power for the whole duration or not. So in that respect, distribution system reliability is very important and we have to give proper focus on it, right? In order to find the distribution system reliability, there are certain parameters like failure rate, outage time, annual outage duration. So actually, why these parameters are required? Basically, whenever we use the term reliability, it may seem sometimes of qualitative, how much reliability is, maybe a qualitative measurement sort of thing. But unless and until we give some quantitative value, we cannot justify or we cannot evaluate how much reliable a system is. In order to get some quantitative measurement, it is required to have some parameters which will define the system's reliability as a whole. So the very basic parameters are, one is failure rate, that means frequency of occurrence of failure in a year. So suppose we have a system, how many times failure occurs in that system over a period of time, generally concerned a year. That is the rate of failure or failure rate. Second one is outage time. Once a failure occurs, for how long the outage persists there. It may be depending upon the time to repair that failure or time to restore power to that point, like that. So once a failure occurs, how much time the outage persists. Third is annual outage duration, which is dependent upon this failure rate and outage time. So over a whole period of a year, what is the total outage duration? These are the basic parameters. But whenever we are concentrating, we want to have a more clear idea about the system's reliability. These parameters may not be sufficient enough, because how many times, suppose we are considering any system, how many times a failure occurs in the system, that from that knowledge, it may not be reflected that how much load has been curtailed or how many customers or consumers have been disconnected during that period of failure. So in order to have a more clear effect about the reliability of the distribution system, we have derived generally some more customer-oriented indices are used. Obviously, all these indices are based on these basic indices: failure rate, outage time, annual outage duration, along with some other record data. Right? Now, these are the reliability indices used for the distribution system's reliability. The first one is SAIFI, we call it SAIFI also, System Average Interruption Frequency Index. Then CAIFI is the Customer Average Interruption Frequency Index. Similarly, we'll have the SAIDI, that is System Average Interruption Duration Index. CAIDI is the Customer Average Interruption Duration Index. EENS, Expected Energy Not Served. AENS is Average Energy Not Served. E-cost is interruption cost, expected interruption cost. So these are some of the parameters actually which are used. There are some other parameters also, but these are some of the parameters which are used to find the reliability of the distribution networks. Now, to go in a bit detail of these parameters, let us see how they are calculated. We want to, in this discussion, we'll be studying how these parameters are calculated. So, System Average Interruption Frequency Index, this stands for the ratio of total number of customer interruptions and total number of customers served. So, customer interruption means how many times a fault occurs at any load point where customers are connected, multiplied by number of customers in that load point, right? So suppose in the system there are I number of load points. So summation of this lambda I is the failure rate of that load point, and Ni is the number of customers connected to that load point. So if we add up all these multiplication, lambda I into Ni for all the load points, that is summation of lambda I Ni, then we'll get the total number of customer interruptions, right? And total number of customers served is just summation Ni. That is, if we have I number of load, ith load point, customer number is Ni. This way, each of the load points customer numbers will be add up to find the system's customer number. Maybe a network, a part of a system, or a simple radial network, or a whole system like that. Then comes CAIFI, that is Customer Average Interruption Frequency Index. That is given by the total number of customer interruptions divided by the total number of customers affected. Now, the only difference between SAIFI and CAIFI is that you can see the numerator is same, summation lambda I Ni, but instead of dividing by the total number of customers, we will be dividing by the total number of affected customers only. Okay, instead of the system's average, we will be finding out of the affected customers what is the average interruption frequency. Then comes the next term, which is SAIDI, that is SAID, that is System Average Interruption Duration Index. This is the ratio of sum of customer interruption durations upon total number of customers. Now, SciFi and CAIFI were dealing with the frequency of occurrence of failure. That is, they were reflecting how many times failure occurs depending upon the number of customers. Here, this index is based on the duration of the interruption. So, in order to find duration of the interruption, the annual outage duration of any load point is considered, and that is multiplied by the number of customers. So, sum of customer interruption durations, that is at ith load point, annual outage duration is UI. You will multiply the number of customers NI with that, and each of these load points will add up. So this will give summation UI NI. And then we will divide it by the total number of customers. Similarly, we will see CAIDI is the customer average interruption duration index. So this is CAID, sum of customer interruption durations divided by total number of customer interruptions. This is given by summation UI NI. Just as instead of considering the number of customers in the denominator, we are considering the total number of customer interruptions in the denominator. So we'll divide summation UI NI by summation lambda I NI. So this will give the customer average interruption duration index. Next comes average service availability index. So what is this? It's the ratio between customer hours of available service by customer hours demanded. So customer hours of available service means for how many hours service was available to the customer in a year. And what is the customer hours demanded? Obviously, we will be demanding, as a customer, we will be demanding maximum possible hour. We don't want power cut. So maximum possible customer hours is the customer hours demanded. So in a year, total number of years is 8760 hours. So 8760 hours in a year multiplied by the total number of customers will give the customer hours demanded. And if we divide this to subtract the unavailable service of customer hours from the total customer hours demanded, we will get the customer hours of available service. That's why in the numerator it is summation NI into 8760 minus summation UI NI. So we divide it by the customer hours demanded. And coming to the available service unavailability index, average service unavailability index, that is, of course, the total index will be 1. If we subtract the availability index from 1, we will get the unavailability index. This will be the ratio of customer hours of unavailable service, that is summation UI NI divided by the summation of NI into 8760, that is total customer hours demanded. Then energy not supplied. So whatever indices we have discussed till now, SciFi, SciD, CAID, all these indices are based on the number of customers. So we have to have the data regarding the how many customers are there at any load point. So they reflect how much severe the fault is depending upon how many customers are affected. And these two indices that we are focusing on now, ENS, energy not supplied index, sometimes it is also called expected energy not supplied, but is the expected energy in future which will not be supplied. This index and average energy not supplied, they mainly focus on how much load is curtailed, the severity of the fall depending upon the load curtailment. So this is the total energy not supplied by the system. So what will be the total energy not supplied? As we know that energy is equal to power multiplied by time. So load is actually in a term of power, the demand. If you multiply this with the outage duration, that is the time for which the outage occurred. So this load multiplied by the outage duration will give the energy which was supposed to be supplied but could not be supplied, right? So Li is the average load connected to load point I. So Li multiplied by Ui will give the energy not supplied at load point I. If we add up all these energies not supplied at different load points of the system, then we'll get the total energy not supplied by the system. That's why this summation is used. Then comes the average energy not supplied. So total energy not supplied, once we can find it, we'll divide by the total number of customers served, we'll get the average energy not supplied. So these indices actually, whatever indices we have discussed till now, are very important in order to find the distribution system's reliability. And if you have followed the previous lectures, in both the lectures of Dr. Balamurugan sir, we have found that the SIP-SID indices plays an important role in the power distribution sector nowadays. So how these indices are calculated theoretically, we'll have an idea of this in today's lecture. Why this assessment of system performance is necessary? Because once we can assess the system performance based on these indices, it will help to identify the weaker areas. Suppose in any part of the system we are finding that the SIP index is poor, right? It's not what it is supposed to be, but it is quite poor, or the energy not supplied is very high. I mean, it should be reduced like that. So then we can identify for which areas are more weaker, corresponding to the reliability of the system. And then accordingly, we can think of some future reinforcement plans. Again, the existing indices can serve as a guide for acceptable values in future reliability assessment also. If we have some existing indices, we may use them as a guideline to focus that after 5 years, what if we do, if we take these reinforcement schemes, then what will be the reliability assessment indices, whether the reliability at that time will be acceptable or not. Similarly, if we have any previous prediction, if we find the reliability new parameters in prediction technology or science also. So these are the important aspect why assessment of system performance is needed. Then let us take a very basic example of a system, and we'll try to find the indices from this system. This is a radial system. Just for basic analysis, we are considering a system with 3 segments, 3 load points, L1, L2, L3. Suppose at the beginning of each segment, there is a circuit breaker. This cross signs stands for the circuit breakers, right? Though in practical system, in a practical radial network, we may have a circuit breaker only at the beginning, and afterwards we might not. Just for calculation purpose, we are considering this is a 3 segment system with 3 load points and circuit breaker at each of the starting point of each of the segment. And we are given with this first table of data. For line A, the failure rate is 0.2 per year. And once a failure occurs in line A, per failure, time to repair that failure is 6.0. Average. By having past experience or something, we have this data that 0.2 times failure occurs on an average. And once a failure occurs, 6 hours is required to repair that failure. Similarly, suppose we have for section B, 0.1 is the rate of failure, and 5 hours is required to repair that failure once it occurs. For section C, it is 0.15. And once a failure occurs, it is 8 hours required. So basically, the failure rate data is given in per kilometer occurrence, per kilometer per hour basis. So if it is given that for 1 kilometer length it is 0.1, we can consider that if the length increases to 0.2, generally it is directly proportional, and the failure rate also increases like that. So if with this basic data we are provided, then we can find the load point indices. We'll just see the second table can be derived from the first one. So we have this load point index L1, right, of this particular system. We are provided with the failure rate of A, segment B, and segment C. Now, if we concentrate to find the failure rate of load point 1, we have to know how the system operates. Suppose a fault occurs somewhere in this portion, right, in the line A. So what will happen? The since supplies from this line, power will be disrupted at this point. So there will be interruption to load point. And for how much time the interruption will pertain? Until the repair time, until the fault may be repaired. Up to that time, there will be interruption here. So if a fault occurs here, the load will be disconnected, right? So this failure rate 0.2 will come. Now suppose next case, if a fault occurs in this segment, will it affect the load points L1? It will not affect, because if a fault occurs at B, then this circuit breaker will operate and the unhealthy portion or faulty portion will be isolated from this portion. As a result, L1 will not get affected due to the presence of this. Similarly, if a fault occurs at C also, there will be no effect on L1. As a result, the failure rate of L1 will be simply the failure rate of segment A. Okay. So that's why we have just written 0.2 here. And the repair time is 6.0. It will be multiplied by 6 into 0.2 will give you the annual outage duration is 1.2. Now, if we come to the load point L2, then what will happen? If it is load point L2, then now again you consider, let us consider fault is occurring first at A. If fault occurs at A, then what will happen? Power will be disrupted, no doubt. And until the fault is repaired, we don't have any other alternate path to cater power to this load point, right? So this 0.2 will be coming. Failure rate of line A will be coming here. Now let us suppose a fault occurs at B. Then also, if the fault occurs at B, then also this load L2 will be affected, and we have to wait until the fault is repaired, right? So these two is coming together, 0.2 plus 0.1, making it 0.3. Is it clear? Now, if a load point, now if a failure occurs like this, we will not get any effect because this breaker will operate and isolate this one. That's why this 0.15 is not coming here. It's not added up. Now, once we find the failure rate of load point L2 as 0.3, then the outage duration will be 0.2 multiplied by 6 plus 0.1 multiplied by 5, right? So we'll find it as 1.7. 1.2 plus 0.5 will make it 1.7. Okay. And by dividing 1.7 by 0.3, we'll get the annual outage duration per year will get as 1.7, right? Then coming to the third point, L3, load point 3. What will happen to load point 3? Whatever be the fault, wherever it be, at point A, point B, or point C, wherever it be, we will have the load point affected, right? Because it is at the extreme last corner, so no breaker can protect it from any fault in these positions. As a result, 0.2, 0.1, and 0.15 would add up. And here again, the in per year 2.9 it will come. Okay, so this way we will get the outage duration. Now, once we get the outage duration and failure rate, we divide this and get the average repair time of these segments. The repair time will depend upon this column and this column. So with this knowledge, along with this data, now what I have taken this table from the previous one, whatever we have derived. If we are provided with the number of customers connected to each of these load points, like L1, L2, L3, and the average load demand, let it be here 1000 kilowatt for load point 1, 700 kilowatt for load point 2, and 400 for load point 3. We have just taken a basic example. We followed the book of Power System Reliability by Roy Billington. We've taken example from there. If we take this average load demands, these data are provided to us, then we can directly calculate this psi P, psi D, chi D, ASAI, ASCY, whatever indices we have discussed. So what will be the psi P here? We have the, for load point 1, we have the failure rate as 0.2. We'll multiply it with 200 because the number of customers is 200. Then for load point 2, we have it is 0.3. We'll multiply by the number of customers is 150. Then for load point 3, it is 0.45. Multiply it with 100 and divide the total by the total number of customers, right? 200 plus 150 plus 100. Okay. So what we'll get now, if we do the mathematical operations, we'll get that the psi P is 0.289 in this particular case, right? Similarly, if we put the values of psi D, in the equations of psi D, chi D, ASAI, ASCY, if we put the values that we have here, for psi D it will be 1.2 multiplied by 200, that is 1.2 is the U outage duration. Similarly, 1.7 multiplied by 150 and 2.9 multiplied by 100, and we'll divide by the total number of customers. We'll get 1.74 hours per customer year. This way, we can go on calculating the CAI-DI, ASAI. Just if you can remember the previous slides formulae, then by putting those values, the average service availability index, then if we subtract the availability index from the unavailability index, we'll get the unavailability index. Then energy not supplied will be load connected, depending upon not the number of customers, mainly on the load connected, that is 1000 in the first load point multiplied by 1.2, that is the U in load point 1 and outage duration, plus 700 multiplied by 1.7 plus 400 multiplied by 2.9. This way we will get the ENS, and once we get the ENS, if we have the total number of customers, we can divide it and find the total average energy not supplied. Now, what we have seen, if we have the very basic data, we can gradually go on calculating these indices. Now, let us take a simple radial system now. And what will be these systems indices based on the basic parameters given. So what we have seen, generally the data available is that per kilometer length, what is the failure occurring in a year. So let's say this data is given to us. This is a radial system with one circuit breaker only at the beginning of the system and no other. Initially, let us consider that these are the distributor lines, no other protection devices, circuit breaker, isolators, nothing is there. So here, obviously the other important systems in the distribution side is present, that we are not considering upon. We are just concentrating on the circuit breaker, switches and all. So here, let's say section 1, 2, 3, 4, these sections are there and the length of these sections are provided. 2 kilometer for section 1, 1 kilometer for section 2, 3 kilometer for section 3 and 4 kilometer, 2 kilometer for section 4. This data is generally provided. Similarly, for distributor A is 1 kilometer, B is 3 kilometer, C is 2 kilometer and D is 1 kilometer, right? And it is mentioned that the failure rate is 0.1 per kilometer per year. Right? With this basic data, we can conclude that the failure rate, if the length is for 1 kilometer, if it is 0.1, for 2 kilometer it will be 0.2, for 3 kilometer 0.3. In this way, we can write the failure rate. Once a failure occurs, the repair time is 4 hours. It's given. For the distributors, again, the length is given and it is provided that per kilometer 0.2 times failure occurs. So for 3 kilometer it will be 0.6, for 2 kilometer it will be 0.4, and for 1 kilometer it will be 0.2. And once a failure occurs, it needs 2 hours to repair it. Right? With this very basic data, let us try to find the reliability parameters. Now again, we have the section-wise data now per kilometer fault. So what we'll have, we need to find the load points data. Load point A, B, C, and D. Now let us concentrate on this diagram. If a fault concentrating on load point A, what will be the failure rate of load point A? If a fault occurs at this segment, then what will happen? The load point A will be disconnected and we will not be able to restore power to this load point until the fault is repaired. Right? So we are writing corresponding to section 1, load point A is affected. So the section 1's failure rate is coming into the picture, 0.2, and repair time also 4. So multiplied 4 into 0.2 will give 0.8. Now if a fault occurs in 2, then also same thing happens. Power is disconnected, no other protection device is there for isolating fuses, circuit breakers, nothing is there. So wherever be the faults is there connected together, this load point will be affected. It will come under the faulty portion, and unless and until the fault is repaired, power will not be resumed to that point. As a result, all these fault load points are coming into the picture. Now let us concentrate on the distributor. The distributors are also directly connected to the system. As a result of that, all the even if a failure occurs at B, then also A will be in the load side and power cannot be restored unless and until the fault B is repaired. Similarly for the C and D also. So all these things are coming into the failure rate of load point A. So we will be adding up all these failure rates, 0.2 plus 0.1, 0.3, 0.2. All these failure rates will be adding up and the total failure rate will be 2.2 here. Total outage duration will also get added up. It is giving 6.0. And we'll divide this 6 by 2.2 and we'll get the average repair time. This will be the case for load point B, C, and D also, because the total system is connected together from this point, right? So we can see in the table for load point B, C, and D, all these cases, the failure rate, average failure rate, average outage duration, average repair time, all are same. And if we are provided with the number of customers and average load connected, as shown in the table here, then we can find the SCI-FI, SCI-D, CHI-D, all these indices. And these indices we have not shown the calculation again because we have already discussed if all these basic data are provided, then we can easily calculate these things, right? So this way we can have an idea about the indices of the reliability. Now let us see what will be the effect of lateral distribution protection. That means in the previous diagram we had this 4 load point system. Now we are adding some fuses in that particular system. All other things remaining same. We are adding fuses in the lateral side, right? These are the fuses. Now let us again see what is the impact of that. Let's focus on load point A. If we focus on load point A, then if a fault occurs at 1, what will be the case, unless and until this fault is repaired, we will get this load point A disconnected. We cannot repair it. So this is coming, whether there be a fault in 2, 3, or 4 segment in the main line, anywhere if fault occurs, then we'll have to wait until the fault is repaired, because the main line is connected together and the whole line will become faulty and will not be able to supply power to this point, right? As a result, all these things are coming, all these failure rates are coming in the calculation. But there will be a change in the distributor's impact, fault in the distributor line. If a fault occurs at distributor A, then of course this load point A will be affected and will not be able to provide power to that load point unless and until we are getting the fault repaired. But on the contrary, now let us suppose a fault is occurring at this point, at load point B, right? Then what will happen? Since there is a fuse over here, this fuse will get disconnected. This fuse will disconnect this faulty portion from the healthy portion, and this portion, this total portion after the fuse will get disconnected. This is the faulty portion, and that other portion of the network will not get affected. So we can see that same will be the case if there is a fault in C or a fault in this portion D, right? That's why this effect of lateral portion B, C, and D is not coming in this picture. As a result, the average failure rate will reduce. This is a improvement sign. Annual outage duration will also change, and the annual repair time will also change, right? Similarly, if we come to this segment B, what will happen? Load point B, again, if any fault occurs in the main line segment 1, 2, 3, or 4, load point B will be affected. But for the lateral distributors, other than load point B, a fault in any other portion will not affect the load point B, because the fuse will blow and will disconnect the faulty portion from the remaining healthy portion, making the remaining healthy portion unaffected by the load point. Okay. So from there, we can calculate again the data, number of customers, average load connected is remaining same. Only thing we have made change is this one. So as a result, we can calculate the Psi-P, Psi-D, Chi-D, all these indices. Now, if you compare with the previous one, we compare this index from the previous slides, we'll see there is an improvement. Previously, the Psi-P was 2.2 interruptions per customer year. Now it is 1.15 interruptions per customer year. Since we have introduced this lateral protections, fuses, the interruption number decreases. So it is a sign of improvement, right? So in this way, we can see improvement in the other parameters also. Then, now in this diagram itself, along with this, let us incorporate some isolators. Okay, in the same diagram, along with the fuses, now we are introducing some isolators. Isolators or disconnects, they are also known as switches, disconnecting switches or something. So what is the function of these isolators? They, in offline mode, they can disconnect or isolate the healthy portion from the faulty portion, right? So in each of these points, we are having an isolator installed in segment 2, 3, and 4. In the beginning of these segments, we are having this. Now, again, let us see what is the change in the indices of the load points. For load point A, we are finding that, again, let's say in load point A, fault occurs in 1, load point A will be affected. Even if fault occurs in 2, load point A will be affected. In 3 also it will be affected, 4 also it will be affected, no doubt. The failure will be there. See, isolators cannot instantly in on-load condition, it cannot isolate the things. these switches cannot operate and break the healthy portion from the faulty portion. But what it can do is, once the circuit breaker operates when a fault occurs, then these switches can be operated to cut off the healthy portion from the faulty portion, and power may be resumed to the healthy portion much before the fault is repaired, right? So if a fault occurs in segment 1, then the system will be affected as earlier. I mean, failure rate will be 0.2, it will be coming, and unless and until the fault is repaired, we cannot resume power to point A, so the repair time will be 4. But whenever a fault occurs in segment 2 here, this will have some different impact from the previous discussions because of the presence of these isolators. What will happen? The moment a fault occurs at this point, the circuit breaker will trip. So every time power will be interrupted. As a result, the failure rate will repair same, just as earlier. But once the fault occurs, once the circuit breaker operates, after that, by operating these switches, this portion, a fault occurs here in segment 2, so the faulty portion, this total portion, can be isolated from the remaining portion and power can be restored to point A. Only time required to restore power to point A will be the operating time of the switch. Let us consider here that it is a manual switch and it takes half an hour to operate, because operating manual switches have several constraints also. You have to identify where the fault is. You have to send the persons, if they're to be sent to that particular location, and isolate the faults and all. Let's say for this example, the average timing for switch operation is half an hour. So 0.5 we have considered. So obviously the repair time of this segment was 4 hours. Instead of that, we need not wait for 4 hours to restore power to point A, because within half an hour we can isolate this segment and restore power to point A. These things are known as basics of electrical engineering, but we will just applying this to calculate the indices, how they are affecting the indices. So the repair time now is changing to 0.5 here. Again, the same will be the case when a fault occurs here. We can restore power to point A only after isolating the switch, faulty portion by operating the switch much before the fault is repaired. So in each of the same is true for fault in segment 4 also. So in each of the cases, we are getting the repair time reduced, or it's not repair time actually, it's restoration time to resume power to the load point. That is much reduced. As a result, the outage duration will reduce, and this will improve the overall system indices. Same will be the case when we'll concentrate on load point B. Let's say here now we are having the load point B. So what we'll have when a fault occurs at 1, you will have to wait until the fault is repaired. That is 4 hours. When a fault occurs at 2, then also, since it is in the upstream side, power is flowing from this side. This is totally in the faulty portion. So until and unless the fault is repaired, there is no other way of restoring power to the load point, right? So we'll have to wait for 4 hours. But if a fault occurs here, then we have to wait only for the operating time of the switch and then can restore power. As a result, the restoration time reduces to 0.5, and hence this is affecting the overall outage duration also. It is improving actually, right? This is true for load point C and load point D also. And if we try to understand the distributor's impact, that this distributor segment's impact, again due to the presence of fuses, only a fault in the segment itself, the distributor segment corresponding to load point A, if a fault occurs here, only then it will be disconnected and it will have to wait for the power to be restored. That is for repair to be done. But for others, they will not at all get affected. There will not be a failure also because the fuse will blow away. As a result, they will disconnect the system from the other portion. So total load point A's value is calculated as 1.0, then 1.5, 1.5. For load point B, C, and D also, we'll find it as usual. Now again, if we use the same formulae, we can find the psi-phi, psi-d, and all these indices. We can compare it with the previous indices. You see the psi-phi will remain same. In previous index also it was 1.15. Here also it is 1.15. Why? Because the failure rate is not changed. It cannot stop the occurrence of fault. Instantly it will be interrupted. So number of interruptions cannot be changed by incorporation of some extra isolators in the system. So the psi-phi will not get changed, but there will be a change in the psi-d. You see here it was 3.91. Now it is 2.58. It is improved because the duration can be reduced by isolating the faulty portion much before the repair is done. Right? Similarly, KID, ASUI, ASAI, average service unavailability index, that also from the previous one, it is much more improved. Energy not supplied will be improved, and average energy not supplied will also be improved, obviously, because the number of customers is same. So if we divide it, we'll get it improved. Right? So this way, we can have an idea about the basic protection devices, fuse, isolators, circuit breakers. These are known to all of us. If we introduce all these things, how the parameters values are changing. We can see these effects directly on the indices by comparing the different characteristics. Right? Now let us see. Till now, whatever we have considered, we thought that the fuses, isolators, circuit breakers are 100% reliable. That is, whenever their function is to operate when a fault occurs, and they will operate that things perfectly, right? But it may be the case that fuses may also not be that much 100% reliable. They may also malfunction. In fact, any of these protection devices can malfunction. We are just taking an example with the fuses. So now let us suppose that the fuses are not 100% reliable. Their probability of functioning properly or reliably is 0.9. Let's say, just an example. And for 0.1 probability is there where the fuse does not operate. The fuse fails to operate. Right? Any device has may fail, may malfunction. So we are taking that into consideration. If we have to take that into consideration, then again there will be a change in the failure rate. Now it will be degraded. Till now we were ideally considering all the equipments that we have are operating ideally perfectly. But practically this may not happen. We are taking that into consideration. Taking an example of the fuse. So failure rate is, then what will be the formula for failure rate? Failure rate when the fuse operates, right? Multiplied by probability of fuse operates, plus failure rate when fuse fails, given fuse fails, multiplied by probability of fuse fails. That will be the formula for failure rate. Applying the concept of probability. With this consideration, let us again find the load point indices, right? For load point A, again, let's say, let us consider each of these points. If a fault occurs at 1, it will be 0.2, 4, and U will be 0.8. Nothing changes occurring, it's same. For fault occurring at 2, 3, 4, all this will be just as same as earlier. Only change will be there when the fuse has an impact. Where the fuse has an impact? Fuse are impacting whenever the fault is there in the distributor segments. Coming to this portion of the table. So let's say distributor A. So here again, for load point A, if a fault occurs in distributor A, there is no function of fuse to prevent the fault or to improve the reliability for load point A at least. Because whenever fault occurs at distributor A, load point A is directly connected to that distributor. So that will be affected and power will be resumed only after repairing, right? But whenever fault is occurring at load point at distributor segment B, previously previously, if we go back to the previous slide, what was our concept? The fuse will operate. This will isolate the segment B, and there will be no effect on segment load point A. Load point A will get undisturbed power supply continuously. That will not be disturbed by this fault because there is a protection device here. So we had, if we go back to the previous slide, we'll see we didn't have any contribution of the failure rate of load point A from the side of distributor B. Why? Because we considered the fuses are 100% reliable. They will be performing their intended function properly. But now, since we are considering this, the fuse may also fail. So that will come here. Distributor segment B may also have some of its contribution towards the failure of load point A. So what will be that contribution? How will you calculate the failure rate? By using this formula, failure rate when fuse operates. So when fuse operates properly, fuse of load point B operates properly, then the failure rate of load point A will be 0 due to fault in distributor segment B. So this portion will not come. But failure rate when fuse fails, if the fuse fails, then of course this will get faults. So what is the failure rate when this fuse fails? If the fuse fails to operate, then we should consider there is no fuse here. In that situation, the failure rate of this segment will directly come. That is 0.6 was the failure rate of this segment. This will be multiplied by the probability of fuse fails. So what we have considered in this particular example, the probability of fuse fails is 0.1, right? So it is 0.06 here. Okay. And as a result of that, the failure rate will be this. And once a failure occurs here, we can isolate the fault by operating this isolator, and the repair time will be 0.5, and accordingly unavailable outage duration will be multiplied by this. So this way, each of these segments will have a probability of contributing to the fault of load point A, considering the situation when the fuse fails to operate properly. That is, the fuse, considering that the fuse may malfunction. So with that respect, if we start calculating this, the reliability of these indices, we will find that again we can calculate the various indices, Psi-Phi, Psi-T, Chi-T, AS, UI, all this. We'll see there is a degradation compared to the previous slide. Previously it was 1.15. Now we are being a bit more realistic, considering that all the systems might not operate, all the components might not operate properly. So with those things, if we start considering, we'll get that the reliability reduces to some extent. And this is the practical scenario. Actually, it's not ideal condition. So these are some of the examples from the very basic parameters, how to calculate all these indices so that we can get an idea about the overall reliability of the system, right? Now, as we are discussing about the effect of switch, so what are the switches? These are the devices which can isolate or connect different segments of distribution system, right? Switches may be either normally closed switches or it may be normally open switches. Okay, so whatever switches we have considered in that previous diagram, that was normally closed switch, because under normal operating condition, the switch is closed. Only if a fault occurs, the switch operates and isolates the faulty portion from the healthy portion. But there may be another type of switch which are known as normally open switches. There are the tie-line switches. So under normal operating condition, those switches remain open. Only if a fault occurs, they can be closed, and they can provide an alternate path for the power to be restored to one particular specific load point, right? So both these two types of sources may help in improving the system's reliability, right? And one more thing, since we are moving towards the world of automation, with the improvement in automation, there is more use of remote control switches, right? In the example which we have considered here, where manual operated switches, and we have considered that 30 minutes of time on an average is required to operate those switches, just as an example. But in practical, for manual operated switches, we have seen, if we visit the distribution sites in the village area or the suburban areas, we can see that it may take hours also, because it depends upon many factors. Whenever a fault occurs, they have to be informed from the consumer's end. Then depending upon whether skilled persons are available in the distribution site at that time, depending upon whether the vehicle is available to move there, all these things comes into the play in practical scenario. And after that only the fault has to be, the switch has to be manually operated and all. So it may take more than hours also. But if we can make automatic switches, so remote control switches, which can be controlled from the remote end, then the time of operation of switch may be reduced to a great extent. And if the time of operation, that is R in our calculation, can be reduced, we can see that a total reduction, a huge reduction in outage duration is obtained, and as a result, we can give more customer satisfaction, which is a requirement of the day. So we are moving towards the use of remote control switches nowadays. Then again, if you consider this diagram, this is a 33-bus IEEE test system, having a circuit breaker here and fuses at these 4 distributors. So we are having all these 33 load points. In the first diagram, this is a basic 33-bus system with a circuit breaker and fuses with no switches. Now suppose we are incorporating switches here. 4 switches we are incorporating in this system. So what will be the impact of these switches? We can understand. Suppose a fault occurs in between point number, let us consider in this segment a fault is occurring. In between segment 16, load point 16 and 17, a fault is occurring. What will happen then? In any load point, let us consider to the load points when a fault occurs here, all these load points starting from 13, 14, 15, 16, 17, 18 will be affected, right? Because this fuse will operate and this portion will be isolated from the remaining this portion. But each of this portion, 13, 14, 15, 16, 17, 18 will be affected because it is connected together. And fault will be restored only after the repairing of that fault. Power may be restored. Now, on the contrary to that, let's come back to the second diagram. We have now a switch at this position, right? In between load point 14 and 15. Again, let's say the fault is occurring here in between 16 and 17. Just the earlier condition, whatever you have considered, the fault is occurring here in this point. Now what will happen? Again, the fuse will operate. It will isolate this portion. But now, after that, since a switch is present here, this switch may be operated and power can be restored to load point 13 and 14 much before the repairing of the fault, right? If it is manual switch, then also much before, and if it is remote control automatic switches, remote control switches, then it will be much more, even much before the fault is repaired, it may be restored. So if we see about, if we concentrate on from the perspective of load point 13 and 14, the customers of load point 13 and 14, their impact, the reliability of the system from their perspective has improved to a great extent due to the presence of this switch, if a fault occurs in between 16 and 17. Similarly, you can consider any other fault occurring at any other point and the effect of these switches. Now, if we try to analyze this, it may appear to us that a switch at every, obviously, a switch at every, more the number of switches, better will be the reliability. It can isolate quickly wherever it is. Suppose we had another switch here, obviously any fault here would also have been resulted into restoration time less. So obviously, if we increase the number of switches, the reliability of the system will be improved. But again, the cost comes into the picture. The switches are costly devices. We cannot have innumerable number of switches. We may have limitation on our expenditure. We may have to compromise with the number of switches because we cannot spend beyond a limit, right? if we have a limitation on that, on the number of switches or something like that, then comes the importance of allocating those available limited number of switches at proper places, right? Suppose we have only 4 switches, we may, instead of allocating in these 4 places, we have randomly allocated now, to take an example, we may allocate it at other places also. There is n number of options to allocate. Now, which position is best so that the reliability may be improved to the greatest extent? That is one very important subject of research in order to improve the reliability. Next, as we have seen that we'll be discussing on the distribution systems impact also. We'll just discuss in brief about this. As we all know what is distributed generation, with the deregulation of the market, there are many generation of electrical energy in the local distribution levels also by the non-utility generators. So these are known as distributed generators. They are generally small generators scattered throughout the system, right? So whenever we are having distributed generation, they may act as an alternative source of supply. If there is any problem from supply from the main end, from the grid end, we can use the DG as a source of supply. When the DG will be able to provide power, when interruption occurs in a load point due to a fault in the upstream of the load point, then in absence of the DG, power will be restored only after correction of the fault. But whenever DG is there, then we may have a second option of restoring power, right? If a fault occurs, but that second option depends upon some condition. First is the fault has, if a fault occurs in the upstream of the load point and the fault is having a switch in between the fault and the load point. If a switch is not there, the load point itself will come in the faulty portion. Again, if a DG is present downstream to the fault point, second requirement is that along with the requirement A, we need the second requirement also to be fulfilled. That is, a DG is present downstream to the fault location and it is isolated from the fault with a switch, right? If these two conditions are fulfilled, the time to resume power to the load point may be reduced. I mean, it may be reduced to the switching time only if power from DG is available, if we have sufficient available power to be catered from the DG. Let's see with this diagram. Again, the previous 33 bus system we are considering, and we are considering 3 DGs at these 3 locations, right? So what will happen here now, if we are, suppose, let us consider on this DG connected to load point 18. Now suppose again a fault is occurring somewhere, let's say somewhere here in between 13 and 14, fault is occurring, right? Now if the DG were not present, for a moment, let's say that the system is not having any distributed generator connected to 18. Then what would have happened? If a fault occurs in between 13 and 14, we must have to wait for the fault to be repaired because we don't have any alternate path of power supply to this load point. Let's say load point 16 we are considering. Let us say this load point 16. So if fault occurs here, we have to wait for the fault to be resumed, repaired before the power to be resumed at load point 16, right? But now let us introduce this DG having sufficient capacity to cater the power of load points like 16, 17, 18, 15 and all this, right? So in this situation, if a fault occurs in between 13 and 14, then obviously initially the breaker will operate and trip, the interruption will be there, but after that, by operating this switch, we can isolate this portion, 15, 16, 17, 18 load point from the remaining portion, and this may act as an isolated load points supplied by the distributed generator present. Obviously, if the other criteria is fulfilled, that the DG is capable of supplying power to all the points and all. So this way, the presence of a DG can reduce the interruption duration. And again, the same thing, you can think that presence of DG, more the number of DG, more the capacity of the DG, better it will be. Maybe it may give such a notion. But again, some other constraints are there, penetration level, and so many other technical constraints are there. But we are not entering into those constraints now. Forgetting other technical constraints also, cost is also a matter. Let us focus on that. So we cannot have innumerable number of DG of very as much size as we expect. So with limited resources, again, if we want to allocate these things, we have to go for the optimal location. Where should this be placed so that the reliability may be improved to the maximum possible extent, right? So with this, these were the basics, and having these basics, we have applied these things to some of the solve some optimal allocation problem depending upon the focusing on the reliability perspective. I just want to show you a little bit so that we can understand how can we apply the basic concepts to solve such research problems. So here one problem is there, allocation of remote control switches in radial distribution system. So what we have considered here, our objective was to reduce the cost corresponding to the energy not supplied. Whenever energy is not supplied, that will result into some loss in terms of monetary values, right? So we want to reduce that cost. So the objective function is there, minimize EENS, J being the load point number. So if you have the n number of buses, so from 1 to n, if we summation the EENS, this will give the total EENS. And C1 here stands for the per unit cost of the energy not supplied. So we have to convert it into the point of money and all, and multiplied by CPV1. CPV1 is actually, this is one way of converting the, since once we are installing a DG, there will be some cost, operational maintenance cost and all throughout the year, throughout a period, considerable period. So CPV is cumulative present value. We are converting all those constraints into from perspective of the present value. So there is some particular formula of converting this, considering the inflation rate in the coming years, then the interest rate of the investment of money, then the load growth rate, and all these things are coming. Considering all these things, we can calculate the cumulative present value, considering a period of life cycle of a year, economic lifetime of the total system or the total installed device. So minimizing this energy not supplied, keeping that in objective, we can allocate the switches. But again, if only this is our objective, then and if we don't have a limitation on the number of switches, we may go for a huge amount of monetary investment on the switches, which is also not desirable. I mean, even if it is desirable, may not be feasible. So we have another cost function where our target is to minimize the cost of remote control switches. Remote control, in this particular work, we have concentrated on remote control switches. So this will be minimizing the number of switches, is NRCS is the total number of switches, and the switches are also having some installation cost and maintenance cost. Maintenance cost will expand over years. So considering a overall lifetime, we are converting it to the present value, cumulative present value in terms of money, then minimizing this cost of RCS. So only this optimizing concept will not have any meaningful thing unless we can combine it with some other thing, because minimizing the cost of RCS will result into, if we don't have any limitation, if we don't have any constraint, will result into no RCS installation. Minimum cost is 0 without any lower limit, right? But that cannot be the case. We are installing RCS. We want to install switches. That's why these two objective functions of minimizing cost of switch and cost of the energy not supplied, we have combined together as a weighted average value, and we have minimized this total multi-objective function in a weighted average aspect, right? So minimize this total function as W into first objective function plus 1 minus W into the second objective function. W is a weighted value in between 0 and 1. And we had some basic constraints like the maximum number of RCS. If we have some limitations, that should not be crossed. And at each one segment, we can have one single RCS. It may be depend upon the designer's perspective, right? And after this, we'll get a number of solutions depending upon the weighted value. This W may be any value between 0 and 1. So we may increase or decrease them in steps. So with all these things, we may use some compromise solutions for multi-objective. We get the best objective value, best compromise solution by applying fuzzy logic theory to each of these objective function, membership function. This is just I'll brief it out because my intention was to discuss the basics and how it is applied. I'll just scroll it over. This is some fuzzy membership function. By using this, then normalized. By using these things, we get a membership value, and then the base non-dominated objective function is obtained. We are dividing this membership value by the total number of non-dominated solutions, total summation, and the best value is taken as the best corresponding solution, right? Then we have applied this concept into two test systems, a 33-bus system and a 69-bus system, right? And we have seen some examples. These are just the single objective function of minimizing the ENS. We have applied different optimization techniques, so we are not focusing on that. So whatever optimization technique we apply, we'll get some optimal value of the single objective functions of RCS and energy not supplied, and the RCS here is coming to 0. And for the 69-bus and 33-bus, I'm just showing these things. And this is the multi-objective result. This is both the objective functions are being minimized together, and we'll get the multi-objectives values. Now coming to the best results, we have got some result of with using different parameters, different algorithms. We need not concentrate on all these algorithms. I'm just wanting to show that if we don't have any limit on the minimum number of RCS, we have kept everything variable. So we have found that 7 number of RCS for the 33-bus system, and the RCS position we have also obtained, and correspondingly we have got the ENS and RCS cost and total cost. This is to be the best result. Similarly, we have got it for 69-bus system also. And if we want, we can apply, this is another example where we have applied RCS and distributed generation together. So here, along with the previous two concepts, previous two objective functions, there is a third objective function where we have installed DGs, distributed generation of variable sizes and all, and we have minimized all these objective functions, and of course normalized value of all this multiplied by the weighted values. Again, there were some more constraints on the size of the DG, position of the DG, and number of DG and all. So finally, again, we have obtained the convergence characteristics of the single objective functions like this, and multi-objective functions, 3 objective functions we have shown with 3 different optimization techniques. We found these values corresponding ENS, RCS, DG, ENS, RCS, DG for the 33-bus and 69-bus system. And these are the best results again. In 6 discrete frame positions, number of DG and number of RCS, size of DG, all these things have been varied, and we have found the best possible solution corresponding to these particular 2 systems. So now with this, we have come to the end of this discussion. To summarize, today we have focused on the reliability indices related to power distribution and their evaluation techniques. After that, the basic protection devices, how they are affecting the reliability indices. Then the effect of switches and distributed generation on the system reliability we have discussed in brief. After that, we have just concentrated. I wanted to show you about the allocation of switches and DGs, some research works related to that, and we have found that switch allocation improves the distribution system reliability. And if we allocate switch and DG together, it improves reliability greatly. And why we have gone for this multi-objective? Because cost associated with DJ and switches are very high. So if we only focus on improving reliability, the cost may go very high. Hence, multi-objective giving a compromise solution may be provable to give more feasible results. So this is all. These are some of the references that I have used. And this is all for today's discussion. So if anyone having any question, I can take those. I wanted basically to focus on the basic ways of how to calculate the parameters, because we many a times nowadays we come across the indices like SciFi, SciD, all these things, but we might not have that much knowledge of how to calculate those things from the starting from the very basic data, minimum data available. So I hope if you can understand something, that will be good. I'll be happy. And if you have any question, I'm ready to take questions. Thank you. Any questions, sir? So I'm stopping the sharing.
Thank you, ma'am. Ma'am has explained the basics of power system reliability. Actually, reliability is one of the major factors in planning, design, operation, and maintenance of electric power systems. So it's essential to know the basics of this. Ma'am has explained the need of reliability studies, what's the definition of reliability, and she has explained the various reliability indices also, like LOLP, SciFi, SciD, and the various calculations with examples. So there are some discussion regarding the fault, how fault is occurring, and what are the failure rates and all, with a lot of examples ma'am has explained. Surely this will help the research fraternity who are working in this area. Thank you, ma'am. Thank you very much for this. And we'll be having the next session by 11:30 a.m. Thank you all.
Thank you.
হ্যাঁ 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 আসছে, এখন আসছে। Oh, network problem. No, it's not audible.
Am I audible now, sir?
Yes, now audible.
Okay, sir. So you may share your first slide.
Okay.
Okay. So, good morning, everyone. Welcome back to the second session of today's lecture. The present speaker is Professor Nidul Sinha. Let me give a brief introduction about Professor Sinha. Professor Nidul Sinha is born in Tripura and obtained his BE degree from electrical engineering from Tripura Engineering College, now NIT Agartala, in 1984. Then he worked in Calcutta Port Trust as a trainee before joining as a lecturer in Regional Engineering College, now NIT Silchar, in 1985. He obtained his M.Tech from Jadavpur University in Power Apparatus and System from IIT Delhi in 1989 and PhD degree from Jadavpur University on application of intelligent techniques from power system optimization in 2003. Professor Sinha obtained LLB in 1994. Presently, he is working as Professor HAG, Electrical Engineering Department, National Institute of Technology, Silchar, Assam, India. He is having more than 33 years of teaching and research experience. He has published around 96 international journal and conference publications like IEEE Transactions, IET, Elsevier, Springer, Taylor and Francis, and so on. He is a peer reviewer in many journals like Applied Soft Computing, IET, IEEE Transactions on Power Systems, IET, GTD, Elsevier, and many other such journals. Sir has given a number of technical lectures in various institutes across India, and his area of interest are power system optimization, automatic generation control, under conventional environment, application of subcomputing techniques, forecasting, case-based reasoning, intelligent instrumentation, and such other. So we now request Sir to start the session. Sir, please.
Good morning. Thank you, Dr. Saheli Rai, for the introduction. My esteemed colleagues and dear participants, many of the participants, it may be third or fourth time of attending my session. So I'll be touching on some new concepts or new ideas or new topics which were not discussed earlier, or sometimes because of shortage of time I just skipped it, and together with that some more discussions on specifically that the area of application of intelligent techniques there, and where do we lack, or where that there are not much things or efforts being made, whereas lot more impressive or efficient algorithms could have been developed and applied for that. It is what so today's agenda is because it is from the previous one that we are talking about, that energy management in distribution system. So some almost similar things together with some additional things which were not covered in the previous lectures, previous talks there, and then that will be, and of course here I'll talk about some of the recent directions or applications of some new ideas for that efficient management and control and management of energy system and distribution energy in the distribution systems there. That will be followed by some intelligent techniques and some applications. I have taken just few of that, and some of the notes I have just taken as similar to the previous occasions. I have picked up some of the observations or statements of the different journals, specifically that from IEEE journals there, and specifically from IEEE Technical Expert Committee on Distribution System and Smart Grid area. So I'd like to I'll be addressing to that what are the technical aspects for that, what are the different terms and issues and other things there. maybe sometimes what are the things which are missed out when we talk about something like that is there? What is that today's level of achievements or that in the from the point of view applications in the real life system? Then this will be followed by some directions in the this I have taken from the scientifically journal papers only who which is based on that the expert smart grid expert committee group or some of that they have come up with some directions they have given for that where I'd like to add some more things there from my sides there. Because you see that nobody is that expert in totality of that one, even including me also. So that one cannot say that he is expert in that in a particular area or even different area. Of course, that one is there. So this one is the same one have taken from that one is there. So this is a specifically this one is a distribution system which may include the domestic part. In the last talk, I was concentrating more of that home energy management and something and some about that group control and other aspects of the primary controls and others. Maybe I'll just touch upon that some other concepts or ideas which were not talked about that. I'll just touch on that. And together with that, some more aspects of that, which is the recent one, which is very prevalent in distribution energy system, specifically that control and stability of that, to ensure stability of the distribution systems there. So of course, the same one will be applicable for not only for the domestic but also for the commercial and industrial part also. I've got this together. That one basically is what we can say that it's not energy management; it's a distribution energy management system. We can talk about that. Here, same one can be extended for that. You see, somebody has made that there's some classification 10 task. That one has to make it there. So I just look for that there. I'm just seeing that, that every part we go for the replication of that, that this is what we go for the optimization techniques. Here's what that appliance scheduling part will be there. Then one can come up with this type of thing. Must mean maybe that meta heuristic algorithms together with the ANN and some other, that is what they have said about that. It is. So there are okay. I'll say about that. That this part is there. It is something like at the same I was talking about that doing something and so that the paper is published and get good point and something like. See, one has to look for that. This is of course an application of intelligent technique. These are different intelligent techniques are mentioned for that. In terms of that appliance scheduling part, energy and price forecasting part. And then here also it is what these are the things that can be given for that. Okay, then RES the integration part will be there, and this that okay that MILP and this one. This is used for that ANN and stochastic mixed integer programming. That it has to be that one. So that all these things are what similar to me that may be applied in the not only every part of that. It's not that how, because there are the tools there which can be made use of that in the different part of that. So even in this case also, you go for the factory energy management also, that's scheduling part of that. Different type of processes will be there. That all this also means what when you go for that, the same can be applied for here basically. And then here retailing part of that energy management part, that also can be what one can come up with that before go for the detailing, or basically what retailing means you go for the energy market there. So that has to be supplied with a lot of statistical results like your prediction of that one, depending on the variations of that environmental variation like weather and others like that is there, and demand variation. All these things will come for that. And similarly, that this also same will be there for the scheduling part of that different type of which is integration of the processes when you go for that is there. Or normally what okay. This one also when you go for that local grid coordination part also, that has to be also can be made intelligent. Depending on that what when you go for the coordination, that also that depends on that what are the different conditions in that every grid. local grid there. So grid will have, under the grid there will be so many entities will be there. Every part will be there. Like as I said, with the mini grid, micro grid there will be that there will be so many nano grid level will be there, and go for that coordination. Even one grid to another grid also, that requires for that. Lot more varying parameters will be there. Yeah, depending on that, like one has to exploit that intelligent techniques there. I'll just give some of the examples, not probably. Anyway, I could have gone for that. Even every this one that can be applied for that. You can just stay for that there. Anyway, so this is what one can apply for that. Okay, when I'll go for this one is there, probably some part will be explained here itself like that. Same similar one can come up for this type of coordination. Any sort of coordination also that require for that intelligent techniques there. So this is then okay. This is home energy management with respect to particular home or specifically this is for a building, big building you have that. And the community you have that one is there. In the bigger perspective of the same one you go for that is there. So that is what we can say demand response and other things there. Making that consumers effective participants or contributors in the smart management of the distribution system. So that they have to be enabled. Like IoTs and others like this. So you have all that different type of IoTs, and together with that different type of services which may be attained through your clouds. So okay. So I'll just give a simple example of that, how it is happening to that confusing term will be there. Like go for that appliance scheduling part is there. You go for the linear or GA, this is any sort of optimization. So specifically you go for that GA type, that is a stochastic, meta-heuristic type of algorithm. We got the scheduling part will be there. How to make this one is what? This is what scheduling, but it cannot be online one. Appliance scheduling means if you make it online, that means the GA has to be, the performance of GA has to be very fast. Every instant something like that becomes very much, that. So that is the main hindrance for that is there. But one can come up with that, how one can do all these things there. You can combine these two things there. Suppose you generate the different situations, critical situations on different operating conditions of that one, that appliances are there. So under the different conditions, then depending on that one is, so you can't given a particular condition, which one is the best scheduling part will be the appliances. Okay, like that means what you can go for that. I'm talking about GA and ANN, suppose. But here, very important aspect could have been that fuzzy one. You go for expert system, that would have been the best way, because that even a simple person who is not an engineer can be asked to tell about that, means what should just sequences of the appliances for the given the importance, given that they are power rating, given that what comfort and discomfort, all these aspects will be there. Based on that, you can simply prioritize that one is there. It doesn't require on a high level of GA and all this thing. One is there. So anyway, suppose one has to apply for that. I'm not arguing for that person. They have come up with a publication in the journal or something like that, but it can be done. So that is, suppose you have that why this can be done. What that you have suppose 10 to 20 or 50 or 100 appliances are there, or suppose 200 appliances are there. So in that case, scheduling for that among the 200 appliances that will be there. That itself is a combination is a huge one. So that is next to means what it is a foolish job to go for trial and error like that is there. So in that case, probably that meta-heuristic algorithm will prove to be very efficient to come up with the best type of sequences of the scheduling part will be there. That is what there. But the thing is that this link may be different, may differ under different conditions will be there. So every new condition means, so what is the current prevalent conditions may be different than what was the earlier. That is one part is there. But suppose in that condition, if you want to call for that, because this one cannot be applied for online, that one is GA based and meta-heuristic based algorithm. But if one combines these two, means what you go for, come up with the best one there under the different conditions. Suppose 50 to 100 situations will be there, and measure conditions will be there. Based on that, you come up with the best results with that heuristic algorithm there, and then that results can be used for training your neural network. You have that. Okay, that can be done two way. One way is what the meta-heuristic algorithm can be used to optimize the ANN. At the same time means what that results of which is obtained through that meta-heuristic algorithm there that can be used for training the RAN. That is another part. So two-way it can be going for that. Any sort of D also, hybrid D also, that is there, GAN and that one. So, but I feel that the expert system, introduction of expert system, this is the missing part. The introduction of expert system could have made these things much more relevant and realistic and more efficient. That one is there. Similar is the case for that energy, energy and price forecasting. That one. When you go for the forecasting part, will be there. Okay, that NN and other that can be used for that is there, and it is very important for that. So one can come up with a different type of, we can talk about the time series analysis or something. That type of thing is there. When you go for that, NN comes to be specifically deep learning and other type of algorithms. But again, this one, as I said about that NN with that conventional, this is same thing. This is the algorithm which is what which is a delta rule produced by that, which is used specifically for the training the neural network or MLP specifically. These are also, as I said about that, when there is a lot more non-linearities there or randomness there, they may not be in a position to come out with more accurate and characters also there. Given that conditions means what for which it is trained for, that there is variations in the environmental situations and conditions there. So in the parameter variations with that one is there, that may that perform poorly in that cases there. Okay, but okay, that again, as I said about that, even one can come up with the deep learning also. Even deep learning also is based on that, that gradient based. I was talking about in earlier occasions also. That the gradient based learning algorithms are used, and that will limit that the capability of that. Basically, these are also algorithms there which are trained using gradient based algorithms are there, which is more efficient for specifically for the local search for that. But can we improvise? One can go for that. As I said about even deep learning also is using for the gradient based algorithms are there. If they are integrated with that, hybridized with meta-heuristic algorithms there, which are much more efficient in coming out with learning much more highly complex and nonlinear systems there. That will make that that forecasting much more accurate there. This integration also, again, same one as I said about that one. This has to be mixed integer, stochastic, all these things. Why it is there? Because integration will be what it's maybe specifically the integration part, like unit commitment type, something like this. You have which are the processes. Renewable energy sources integration means you have the combination of which sources there under what conditions. Okay, under certain conditions, combination of which units are there. So which units are to be considered or not considered. That means this is it is simply is a integer type, is a n 1 or 0. If it is considered, then it's switched on to 1. If it is not considered, 0. You have that is the combination for that. So first part is which set of which units are to be considered for that. Set of which set of units or elements are considered. That makes 1010 combinations there, and followed by that for each given set of that appliances or that set of units they are integrated together. Then go forward how this integration or they should be what should be the level of integration among all the considered or connected units there. That is your continuous optimization. So that is what we say that first part is integer and next part is what it is a continuous one. That is why you require that mixed integer means by integer plus continuous means one, which is so integer is not continuous. So you have that type of things that can be used for that is there. So one can use for that also is other way like that is there. But this also can be used for that that when somebody combines that basically what as I said about that this one and even this one also when you go for that is there, or specifically this one is a very important part is there. As a very important algorithm should be what that you have to have a neurofuzzy systems there. Some very few limited works are there which have used the neurofuzzy systems there, and which is exploitation of expert system for the given one is there, because we do not have thousands of variations of that one is there, because even thousands of variation we can cluster into some particular set of 25 to 30 to 40 to 50 type of set of conditions will be there that will take care of that most of that eventuality of that, the events are which are normally occur for that to be covered up. So you go for the neurophysical system there. When this neurophysical system will be that neurophysical network or neural network, we can say that one is that neurophysical system will be optimized through your heuristic algorithm. That is a combination of three things there. Meta heuristic algorithm, which is used for optimizing that neurophysical network there, and then only what this is supposed to come out with excellent results for. I don't think that is not much as I said about this. You see that for each one they are coming up with some obligations on this. Similarly, is that one of this one is what they have come up for this coordinated operation with large system. That is okay. Okay, this also, as I said about this, not going to make thousands of conditions for that set, under which what are the different and the coordinated conditions will be there with large systems there, and that also in the every part that will be there. So they have come up with that with Markov process there. That means for some sort of stochastic given the condition of that one, they come up for this one. There is some paper they have just asked for that, but one can come up with it here also. Like this algorithm, when decision making of that one, say decision making process can be made intelligent for that. Not just the way we saying about that one. The same thing can be extended for this also under that different conditions when coordinated operation has to be the large system there. Again, this one is again the energy sharing for that there. Under the given conditions there, one can come up with a different type of sharing. That till now, okay, I'll talk about that today when I'll go for that little bit of that. What is done right now and what should have been done. That part I'll just tell about that, which is not done. That has to be. So somebody wants to do, suppose you propose for the today some projects there. You submit a project today. Why it is not accepted? Because the first hand impression has to be what? That has to be that the objective, or not only that, by name itself, title itself should be appealing in the sense means what? It should have direct societal impact. Impact in the sense means the real life, contributions to that one is there. And at the same time, you have the technological content of the term itself has to be also much more appealing. In the sense means what you ask for the something which is very promising type of offer that's there. So just one has to look for that. Then only you can say about that. From the beginning means what why one has to go for that project there, and it has to be that because of that your technical you can say that one technical merits for the on the methods which are proposed for that, automatically things will be. While implementation, you may not be in a position to be successful in every percent for that. But the thing is, your objective must be much more realistic, much more promising for that. That based on that only, what an expert when we go evaluate for this. Anyway, I am not talking about myself as an expert. I don't want to comment. This is a confidential part. So, but what I say is what share my experience for that. When somebody goes for that evaluation of the technical, proposals being submitted for that, first time we look at that. What is the or topic as such is there, and what are the methods which are proposed for that, and we see that what is the novelty in that one is there. First thing is what is the title of that one, followed by the ultimate objective of that, and what is the method. Whether the just propose anything means what may not be. You cannot say anything like just coming up with that one either, unless you showcase that yes, your one has lot of merits when you are whatever the methods you are proposing for that. So that has to be, with the technical, reasoning, you have to prove that why your method, is considered to be what, or appears to you to be very promising one, so that which is going to enhance that, societal contribution of that, of the technical research part, research output there. So go for that is what. So when you go for that, this one, suppose the energy story multi-service and that different type of we can have that one. So when you go for the sharing of that energy management or specifically sources, not only that, some of the mobile sources, mobile storage, there were like electric vehicles and some others will be having, like you create a situation for that is there, which will be a very lucrative in the sense of what you create a market for this there. Market for that is what you have to. Motivate the consumer. So as I said about the prosumer, there is a term used for that is there. You have to activate for that, motivate that specifically consumers, so that they can take care of that share for that there. means what participate in that. Now the next part is what, okay, it is well talking, when you talk about the smart, and so many people talk about that, that it is a self-healing, auto adaptive, and so many others. You go for that is the one, something like that. But is well said while talking about that. Next question is what level of that you just promised for that, or you keep in mind for the that aim is there. How much of that one can be, or what are the technical challenges to implement for that, or that whatever the technical methods should be considered so that like your objectives are satisfied with a lot of positive outcomes. Of course, one cannot expect for the 100% success for that one. It has to be a long way. One has to go for that. It has to make a beginning and in the right directions and go for any stepwise, go for the improving for that is there. So so that is what one has to go for, that is sharing of that will be there. And at the same time, you go for the demand side management and all this, what maybe also they have done for that. I don't know that this is B is the what go for that N and D and all this is also one prediction of that one to come up for that. Together with D at this one, I know that's what, and N for the specifically what you have to predict the demand and ultimately go for the managing of that. Of course, that predictive algorithms are very much important for the demand side management. But together with that, what there has to be adaptive, there has to be adaptive, rules there, which will make that one that every participants in the management of that one is very, very active and very efficient and very eager to participate for that. So that like ultimately what you can make the best use of that. So indirectly through the pricing, and you target at the persons who are supposed to participate. That's what one has to. What is the controlling? Means motivation is through the prices. If it is made for the market base there, you simply for there is huge market for particular activities there, then everybody will be go for that. There will be heavy demand for that there, and automatically go for that is the one. So, but the thing is, okay. So this thing is what how one can come up. What we do is in these cases we assume there's some conditions there. Based on that, we train the neural network, and then giving for that one is there. Ultimately, you get the results. Okay, it can come up with a more accurate in this one. So that is how means what okay. That of course has to have means some sort of research. Of course, may be good for the beginning of that one is there. Again, as I said, for that when this are supposed to be implemented, the prediction level is where when it is actually management, this GSM is to be implemented for the real time, then there is you can go for that. It's okay for given that one ANN can be, as you know, that ANN cannot be trained for unknown situations there with the different conditions. That similar, okay, not same, similar conditions, okay, it will be intelligent, but very dissimilar it may not be. You cannot say like that. Like even a human being who is not intelligent about something like that, you ask him to give an answer. So he has to look for that means what from his overall experience of that one, he will try to extract that what are the similar things, situations on which what type of actions were taken by the human being, and then what were the outcomes and all this event. But that again, that one is there. So how the neural network, that has to be, you can consider for that how many similar type of events, and that is again that creating a thing like that problem, the limitation. But as I said about that, you go for that neuro fuzzy systems, that same type of that one, you go for that is there. So they means what given the things there, and some of that demonstrated these are some are thumb rule type. It is so much you understand that in the night time there will be nobody to use for the light, nobody to use for that that washing machine. And all these things are so is a common sense based on that one is there, and we expert means there is what that. Many people who are not engineers, they are supposed to share, because engineers' job is not to make that rules and others there. Rules will be made by the person who are having requisite knowledge in the given system. Engineer, it may happen that if a topper may not be, I said about the other day, means what the topper may not have that experience of that, that the theoretical topper may not have even single time experience of a particular real life event there. I cannot expect that he will miserably fail like anything. So this is what the real life thing is there. Who are the person who are, or the people who are associated with the system, they are much more knowledgeable. So engineer's job is to extract the knowledge from them and ultimately implement for that. When you go for the implement, only technical engineers perspective is how this different issues, what is desired by the customers and society, they can be implemented for that. So any techniques which can be achieved for that implementation, some techniques are there. And what are the technical challenges? That is what we talked about. That is there. Okay, so okay, so in that case, as I said about that, I'm not okay. I'll say that because uh, same and the last the kind of talk also I talked about the DC grid is what it is much more easier to have to implement things there. Technical implementation will be easier as compared to that AC microgrid there. So DC microgrid that in that case, of course, we can come up with a lot more functionality which we hope for that or we desire to incorporate in our smart systems. There are different features that can be an easier way. Okay, so but once the moment you go for that AC one is there a lot of complexity come in for that, because you have not only voltage, not only, it's not voltage only, not the because the frequencies, the variation of the signal creates a lot of interactions and interactions among the different elements, different systems like that. That makes that things complicated for that is there. When the system really in operation, that one is there, some situation will arise, then people may not be may not be in a position to understand that what has gone wrong or what are the problems there, because the system as such is complicated for that is there. Okay, so if it is a DC microgrid system, there's not much. If it fault diagnosis and monitoring and fault diagnosis part of that one is there, but isolation again, that restoring for that, all these things will become easier and simpler for that. So this was same as the previous one. Okay, I said about that. That is already discussed for that. That microgrid may be grid connected mode or islanded mode is there. Okay. So the question is what I'll just talk about that is that here I have given that that most in a microgrid condition normally what we consider for that. I'll just say about that. This that three type of converters are there, because nowadays what the use of converters become very prevalent because of the lot of developments in power electronics. So in the last talk I said about that the three types of that grid forming converters. Okay, then what grid feeding and then grid supporting that converters, because so that this because of their that which way that a particular your grid will be working for that, or your that distribution system will be working for that. Okay. So that may be what that or microgrid you can say that, because microgrid is nothing but basically the distribution system there. Or you can say about that, of course, in that case you can have a nano grid there, which also is distribution system there. But that from the bigger scale you go for the microgrid, nano grid, and then maybe what one can think of the picogrid or something like that. So anyway, so that is the one we have that small systems there. It may be made what is grid connected or islanded mode there. My question is what when we're talking about that, one part which was not covered up in the last talk I expected for that is what. Okay, what is that in this mode when it is a grid connected mode, then micro sources are, because the distribution, this micro source means what, the distribution generations are there. Distributed generations, I mean DZs are there, expected to generate power at the rated capacity to decrease the power to be imported from the grid. So this is what we want to relieve that power imported from the grid. Maybe it's just like concept, it's not always true for that, because the grid is always there having used power or something like that. One should not think of that, because grid has whenever the power is available at the grid means what, you have lot more options, that there will be thousands of millions of users which can use for that is there, which can use that the power available at the grid, a bigger grid, the larger grid there. So normal cases what wherever the objective is what for microgrid is what, when the under normal conditions there, most of the power is to be met from the local distributed sources generation generating sources are there. That is what, or sometimes what maybe 10%, 20% of the remaining unbalanced, that one may be taken from the grid is there. That is what we say about that is that tie connector is something like there will be connection or the tie line between your microgrid and your major grid. That is what one can think of that. Okay. Or maybe what there may be what the connection between one microgrid to another one, then another to another one, 3 or 4 microgrids may have to connect it together there in a pool. Then it may happen that all may be connected, having the provision to be connected to the grid, or maybe other way like there is a dependent on that one is there. So so that is what. So in that case, what happens if it is a grid connected one? Then loads will have their that they will have more freedom to consume that one. But the thing is what that This is the grid power assumed to be infinite. So that one is there. They have much more liberty, that to have our options to meet their demand. That is what it is there. So it is not means which has been the case, till now. Till now we have, because we consumers, we think that means the power there is there power cut means or we resent, we express our resentment. It's not other way like that means whatever given to us, whether we are in a position to make the judicious use of that is never thought of that till today. It's not there. That concept has gone out for that is there. So that has to be. So suppose that there is a so in that islanded mode is there. So it is not in this mode. The unavailability of the grid requires a specific management of the. So that is one means in case of suppose there is a fault or some unwanted things happening in the grid. That means, as I say, it means what when it is a grid connected mode, 20-30% of that power is coming from the grid or something like that. Suppose you are dependent on the 50% power has to be shared from the grid or supplied from the grid. Then of course your dependency is more, even 60% is more, something like that is there. Depending on that one is there. When you go for that, you have the provision for management of that one that your grid. There was a specifically microgrid. In the event of if there is any fault or any untoward incident for that makes that main grid to go down there, then ultimately you have to save your systems to switch to that islanded mode there. So you see, there is another aspect will be there which has to be looked into that, So as I said about that, you see, don't think from that only research point of view. You see, suppose you have a microgrid which may be inherently designed in the islanded mode, okay, then it's operational, that your planning and operation and other things will be different. It has to be different. And when it is designed to have both grid connected as well as islanded mode, then its operational strategies and protection, everything has to be different for that. Philosophies are there. The question is what? That when a microgrid which is used for that islanded operation, that the concept of what that the 50 Hz frequency, 60 Hz frequency, and all these things is not much important. I don't know that that the condition of the why India has adopted 50 Hz, why not 60 Hz, and all these issues are coming up for that. That you go on increasing the more and more frequency, then generally what you have that voltages and other things will be more higher and higher induced voltage, and machines will be smaller and all the same. But it has a lot more other issues there. One can come up with that also higher frequency generators and all this, but it has some other implications for that. Who stops for that there? So here also, that we have to think of. Suppose you have an induction motor there, which is 50 Hz. It will be near about the 1500. That one RPM, suppose it is there, and when it is run as that 60 Hz, then definitely it will be much higher. So that means its same machine's output will be much more higher. So that why 60 Hz? Why not 100 Hz? That is what I'm talking about. That is there. So in a conventional system, we go for the large grid there. There are some constraints which are considered, which do not allow the consideration of the 60 Hz, suppose for the developing or underdeveloped countries or something like that is there. But that is not much prevalent for this type of things that we go for this one island. If it is independently islanded, I'm talking about AC microgrid. If you go for DC microgrid, nothing doing. There is no frequency, nothing like that. So simply different for that is there, and you can come up with a lot more options are there. Even that we talked about what that previous days, old days, the concept was that that the transformer revolutionized in favor of that AC as compared to the DC was there. No. Nowadays, what you have the DC is there. So many, that you have the adapters there, and which is capable of converters are there. DC to DC converters, so much efficient, and they are so much reliable. You do not have problems for getting high voltage DC and low voltage DC and all these things like this. So that means anyway, I'm just talking about that. So even if it is an AC microgrid, we do not have much more constraint as compared to that when you go for the large grid is there. Even in the large grid also, anyway, I should consider. Okay, you skip that part. I'm not there. The same is true for large grid also. But under what conditions? Yes, under certain conditions, same philosophy can be applied to that one is there for the large below. There is no point in that. No, there is no that type of measure if the majority of the parameters which were that the limiting for that going for 60 Hz and others even more than that one is that is what that can be removed for that is there as of now, because of so much development in the technology have taken place there that allows for that is there flexibility of this. Anyway, one has to look for that. So we go for that here. So okay, now the question is what when you go for that islanded one is there, unavailability grid requires a specific management of micro sources there and the loads there. That I'll say about that one part of that. Only one example of that how the frequency control scheme has been implemented for that. Whatever I'll show you there. There are slight modifications in that also. One has to go for that is there as of now. Though it is already because I have taken from paper, journal paper or something like that. Anyway, somebody has used for that. It is workable. But the thing is, more efficient and other ideas can be incorporated for that. So okay, that's why it is there. You go for that unavailability of grid requires the specific management of micro sources and the load. You have to go for the specific management of micro sources and generation as well as load, since they cannot simply generate or consume power at their willing. Whatever they desire for that is cannot be. So you have to, because you have the limited, that the sources, micro sources. The problem with the micro sources is what that the energy available with that the micro energy sources that are limited. It's not used. So one has to look for that is there. So in the loading part, the one has to be, as I said, is the grid connected mode, you can be, enjoy the luxuriness of that. Means whatever way, you may not switch off that one is there. But in this case, if you do not switch off that one is there, may result into what, having you to be without power for some time like that is there. Even they will come for that. Okay, if it's a market base, that can be always taken care of that. That can be always taken care of that because again another that question arises for that another part is that one has to come out with the philosophy something like that is who is rich for that he can buy that that he can spend every day 20,000 or something. There is a very rich, so then he will buy all the powers available from the market and he will enjoy, whereas that his neighbor may not be having that money to buy all these things there. So in that case, how that egalitarian or at least what equity to some level in the society can be ensured for that, at least because this becomes the basic necessity of the society there. How one can go for that. If it is totally market based, then again there has to be, so there has to be some more things which has to which has to be incorporated, so that will keep a tab on that limit on that misuse of that part by the limited very potential players, market players or something like that is there. So then anyway that part will be there because that one can go for that. Like suppose if the limit is violated, it may happen that you imply the punishment in the way of what you will not get power for this many hours because of that one is something like that. So you have controllability of the switches are such that means what that from a remote ward. Even a DC, no problem. Even AC also it cannot, because it's a switch. So switching, controlling, and because of the IoT and others, this is not big thing there. If somebody does sabotage, that also can be detected for that, because nowadays softwares are so much capable. Though hacking is also that possibility, then their anti-hacking and other type of measures are also coming up for that is there. So that is how one has to look for that is there. But from the technical part, I'll say for the technical part there, disconnection with the grid demands that the total power generated by the source should be equal to the total consumption. That is there plus losses within this. That is okay. It's the common sense that one has to ensure for that real power balance in the islanded mode there. But the thing is here, one has to look for that, that even if the system or condition requires for that least priority, that one least priority, that loads are they have to be cut down for that is there. And in addition to that, suppose one can come up with that, that demand response type of there. You have that all the loads will be, some will be critical, some will be non-critical, and all this based on that. And one can come up with that, effective measures and all like that is there. And I do this one will make a same thing there. When you go for the logics of that one is there, wherever that you come up with the logics there together, which requires logics, which requires development of which requires that your expertise or knowledge in that particular domain. Again, you go for the expert system there. So that is what is for that. Okay, now I said about that one. Yes, I'd like to address one issue there. That it is emerging renewable energy based disease in the power reduces the total inertia of the system. In last the talk also I discussed about that. When you go for that more and more disease there in the system, or you think about that, it is not that total system smart grid there. We are considering for the microgrid there, which itself is a new system, the independent system, which is designed and planned and designed and monitored and controlled in an independent system there. Because as I said about that microgrid, its connection with that main grid there, that itself can be treated as a tie line. Okay, it is something like you have a generator connected to infinite busbar. So infinite busbar becomes another machine with what infinite capacity, and your generator, local generator, becomes another machine. So it's the two machine analogy for that is there. The same is one can come up with that the microgrid there, which is connected with that main grid there. So you have that same one can be what it is a two area something like concept is there coming up for that is microgrid happens to be what your new area one area and which is connected with another main grid is there. So a Thailand there. Okay, so anyway, so the question is what when you are considering a microgrid there, then that the microgrid is because the power levels are very less, and then again that the renewable or energy sources, energy generating sources or even other type of that one, whatever we got, suppose battery is what it is acting as a source as well as load. So that wherever we have the energy sources there, suppose we got the renewable energy sources, which are more of the mechanical based, the devices there. So that sources are what that the dimension of the sources are very small. So because of that inertia, also system also becomes less. So if the inertia of the system becomes less, now the question is what the power grid dynamics and power microgrid. Power grid means what that the microgrid dynamics and performance can be negatively affected. That this is a load frequency control. So this concept was when we were studying for the automatic generation control in old days or something like that, this concept was never faced for that, because there was that distribution generation was not at all there those days there. It came up for that is there. So this concept is new in the sense of what you have that AVL, that voltage control loop. You got this is particular aspect is very much experienced in the AVL loop. AVL loop, what we do is what to make that that system exciter performance very efficient and very efficient in the form of what time performance there, time response there. So you come up for that means nowadays most of the generators are what they are provided with static excitation system, electronics based excitation system. In those days, not like the other way, like you have a generator, separate generator connected with the DC generator to supply the DC to that field winding or something. No, now you go for that all static excitation system. Okay, so we come up with the static excitation system there. So ultimately, that the AVL loop becomes an static excitation system becomes very fast responding. So when you have a very fast responding one, when a system responds very fast, when inertia is very less. So when you come up with a very fast responding that AVR loop is there, so when it will have that one, then for slightest noise or some other unwanted oscillations also will create what some forces which will be amplified in the process feedback loop, and ultimately what that will also have a negative impact on the stability part of the system and lose the stability. Okay, so most of that one is what that your first excitation system, AVR loop with first excitation system, they experience a lot of instability problems there because of what the negative damping. It is called negative damping. The negative damping. I don't know that. Okay, negative damping. Okay, because the first responding you go for that, the negative damping is there. That ultimately what happens that. Negative damping, and when that specifically this is also very much pronounced when you have that capacity power factor, capacity power factor of the power system. Capacity power factor of the power system is very much unwanted. We not want it. One must know that we prefer, engineers prefer to have lagging inductive power factor to be there prevalent, so that the generator becomes more system becomes more stable. Specifically when you have that zero power factor or capacity, specifically that one, that means it is, and together with that you have fast excitation system, every chance the system will collapse. voltage instability will occur for that. So what we do is, in this case, we use that to overcome this one is the negative damping. We add that, the positive damping to the system in case of ABL. So what is the positive damping is nothing but what that we go for that. This positive damping is what we go through the power system stabilizer. You might have studied for the, some of you might have heard about that, the power system. So it's basically what we add that phase compensation device there, the power system. So that power system, the stabilizer is nothing but it adds to that the positive damping to the variations in the voltage, variations in the voltage. Okay, so delta V or delta V by T, so at that time rate of change of the voltage deviations there. That is what that. So that means what it damps out that negative impact will be damped out for the positive effect of the positive stability. Means understand means, oh, what is the meaning of that? That means we can think of that dynamically. That negative damping means what? That is because of why the negative damping caused the faster response from the first acceleration system. So it responds very fast. So that creates a negative damping. So we want to what? What is the positive damping means? What we go for? What? Slow down that. We want to slow down that that fast responding technique is, that is what we go for the positive damping. We go for how much that one has to tune for, that is the gains are to be values are to be tuned for the optimized, so that like for a given system under the conditions of the range of variations of the parameters there, system performance is stable. Same is the concept in case of what in the DCs there with this DCs, because they reduces the inertia, so the response is very fast. In the DCs, for when there is disturbance to the real power balance, that results in what oscillations in the system, and that oscillates very fast, So so before that you resort to that any sort of damping for that, is there, then one can means immediately what that it may be the value may be rise to that extent that for that system may go out of there if proper damping is not provided to the system. So damping may be in the different way. One can come up with that that you have the different type of storage elements, device loads, and also so DBR and all these things that type that there. That is what, of course, there's that are coming for that. So one has to come up for that is what to so all whatever go for that DBR and others that were that so all this one also they are also indirectly what they are going to negate that or cancel out that the negative aspects of that faster responses for that or because of the small inertia of the system. Okay. So to address these issues, several inverter methodologies. This is possible. That this how one can go for there is there. Different techniques are provided for this there. So several inverter control methodologies have been recently proposed for the DGs there. A lot more things are coming up, also new things there. As I said about that, this inverter control methodologies also can be made much more efficient. I don't know that I'll have to just skip some part. I'll just talk about some of the things there. Okay, still time is there. Okay, so what is that? Is some of the recent one concept is what that which is done for introducing the concept of virtual inertia and then better understanding of the dynamic characteristics of the power networks in the presence of high penetration of DCs and renewable energy sources, basically. Okay, so because this so sources and that one is there. It is when you go for the high penetration of DCs and renewable energy sources for that. Okay, again another one a misleading concept is there. That talking about that. That when we say that one, that introduction of this is what saying one I said about that. What one will understand for that? What one will understand that introducing the concept of better understanding of dynamic characteristics of power network in the presence of high penetration of DCs and RESs. Means what one talks about that power network is the grid network, the large grid network in the presence of high penetration of DCs and RESs. What I said about that, you consider about microgrid, independent microgrid in the islanded mode, then there is a concept of what that reduction of that that reduction of inertia and all these things there. But when you say that one is your microgrid happens to be a part of your constituent of the large grid is there, how that that inertia will be less? This is the question. You see, suppose I require 1000 megawatt. Okay, So out of 1000 megawatt, 100 megawatt or 200 megawatt is met from my own there. I have a my big large grid is there which is having a 1000 megawatt capacity, and out of that I have my DG system is there, which can be or not DG system, like a distribution system which can be treated as a what 100 megawatt, okay, system there, microgrid there. So that one is what one thing that one has to think about, that means 1000 megawatt means what one has to say, that means 1000 megawatt minus 100 megawatt of the DGs. That is one part. That so balancing will be what the so means ultimately what that inertia of this disease and renewable energy sources are to be added with the inertia of the remaining what 900 megawatt of the generators which are bulk generators which are used for producing that one. Then how can say that one is what it reduces that, a better understanding of that is there. Okay. Anyway, that part one has to look for. That is that when you go for the local mode and that remote mode is there. There is a concept of what is the coupling coefficient. Or coupling coefficient means what in between that you have a generator. Suppose you have the 10 generators there, okay, which is producing 1000 megawatt there, and you have DGs there or 10 DGs or something like small capacities are there. So the coupling coefficient between these two are dependent on that one is what impact of the DGs on that one, main generators, all these things which will be coming for that. Anyway, but as I said about that, okay, that may be also thought about other way also, like there is there. Well, the current one can think about that. Anyway, okay. So if you think about that one is what as I said about that 70 to 80% which is met from the DGs there locally one. There, the ultimately what for the microgrid part will be there. In that case, what that the inertia will be very, very small from that point of view system is there. Okay. So anyway, so here what happens there? Question is what that the concept of virtual inertia. Okay, that concept of this one, the virtual inertia, which is the concept which is being used for that, which can be that is a virtual. It is not the actual machine. So when you have the actual machine there, that means this is a generator because which is having a what mechanical that which is a mechanical elements there, and we cannot change our mechanical elements of that one unless and until we modify the design itself. Can we change the design which is in operational condition? We cannot. We cannot change its mass and other things there, which is already once it is designed. So, but the thing is, this concept of virtual inertia is what which gives the similar characteristic of the synchronous generator having that one is there. So, which can be modified because it is a virtual one, can be modified depending on the necessity of that. What is the necessity? Is to introduce positive damping to that one is there. So, when this lot of response, that very fast responding, responses come up because of that small inertia of the system there, because of any interference or disturbance there, which can be damped out for that is what this one will absorb for that. The first part will be there, so that which will go for the some sort of positive damping in the systems there, and depending on that, so it can be made so that okay, okay. There is one also again that one is another concept means that one is there. The VSCs are being used. Okay, I said about that. That other day I was talking about that. That you have a one grid connected with that. Even today also I talked about that. You have a large generator. Is a synchronous generator there. Okay. So after that generator, what happens here? That generator you step off that voltage, and after that you have that. What is that? You have that generator transmission line, and from one side and another generator on the other side of the transmission line connect for that is the AC line. Why AC line? It may be AC line, but the thing is what you make that your system or the transmission system independent of what is the speed of the generator is there. How you can go for that voltage? So the converters will be there. You use for that. When you have the power electronic converters there, you are free to it will be made in some sort of is what is it used in the modern power system results in the decrease of inertia again. So what happens? There's the interface through that voltage system, but there's no power electronic converters will be there. Then that will result into again decrease the inertia. That why decrease of inertia? Because now is what other system doesn't see that what is happening to the generator. It is seeing only up to that what that the source which is producing the AC. Who is that one? Is that converter there? Okay. VSC is there, which uses for that. It's a power electronic device. It's a very fast for that. So that means here we can change the frequency the way we want. Means what? So we can have that frequency means nothing but that voltage as well as frequency can be controlled very fast, very way, without that. Of course, that interface has to be, the algorithm has to come up for that between the real power synchronous generator and that one is there. So, but that makes again that one decrease of that. When you go for the power converter, in future this will be the reality. As I said about it, come up for that one is there. Then in that case it will be result of inertia, and again that one is frequency instability will be there. Because when there is a lot of the too much faster response will be there, because of minor changes, the disturbance in the real power imbalance, that will result into variations in the frequency, and you have that some of the relays are there which are made to respond because of that, the variations of the frequency there, because it is treated that, of course. Okay, another concept is what, that the issue of frequency instability again, it is not that this concept issue is not much stringent when we think of actually all mechanical electromechanical system without any power electronics device. There whatever the factors we consider, but here whatever the factors we consider, but the parameters will be slightly different. It's not same, because in those case there, if you go for that is there, if the interface between the real power generator, synchronous machines, and that your VSC converter there, and because otherwise what, there will be interaction between the VSC at that one end and other side, and the VSC at the other side of the one side, and then VSC at the other side of the transmission line. So ultimately one can do that, lot more options and lot more flexibility for that, independence for that is there. So now the thing is what that, but the thing is, this will result into what, that response maybe what, the response will be very fast, and the result into instability of that one is there. So one has to look for that. This is the techniques for this one will be different than whatever techniques which are followed the completely mechanical system without power electronics device there. Okay, anyway, the reduced number of synchronous machines and that one integration of the wind turbine, that means that you come up with that most of that renewable energy sources via that converters there. Then again that one is there in that one system with the decouples the rotational elements, physical elements from the grid. You have the grid microgrid there. Hence the reduction of inertia in the system threatens again frequency stability. So the virtual inertia is a solution for this type of things one. So because that one lot of negative damping is there, that creates our frequency, may create frequency stability there. As I said, means what, this problem occurs only what, again the frequency stability of that this one concept is what again relevant when a system microgrid is designed specifically for the local one. This is not much important for that is there. One has to look for that. Why the frequency, why the stability level, the limits of frequencies are considered for that is there. Look at that one, arrived at that one. So the parameters and the paradigm conditions, the decisions are not same. Okay. Anyway, so virtual inertia is a solution in the described premises for that is okay. This one there. So virtual inertia for that anyway. I have just given for that is what is the virtual inertia for that is there. You have the energy source there. You have this the virtual inertia for that is there, which has to have a what energy source. It has to have energy storage and then inverter. That energy source, energy storage, inverter, and the control mechanism there. So that will be what you have a one. Some the dynamical functions will be similar to the swing equations of the synchronous generators will be embedded in. So the ultimately what for the given input or the input and output this power is there, and you have that one equations which will be behaving like a synchronous machine, synchronous generator, and then so that like power outputs of that one, and because which will be based on the grid measurements of that frequency and polarity, and then there what the rate of changes of that one based on that for that is there. So ultimately what one can modify that. One can modify the responses of that given that, because this is based on what algorithms you have that, and then just storage devices very fast responding in that case. That when you use any emulator or develop an emulator there, and where that every element is very fast responding, then that type of that emulator, when that emulator can be made to mimic that any system which is very slow. Of course, not faster than that. Very slow, any variety of that. What is there? So what? It is simple through algorithms on. So variation is very fast that way. It's a very flexible and other way. Okay, that is why this is the advantage of that. One has to come up with that. Anyway, I'm not going for that. Okay. This one I have just given for there. Some updated scheme is there. Okay, I have just taken from the journal there. They have come up for that is there. Demand response part or the demand control part will be there. This is what again. This is inertia control. Say about that. The today's one has to have the microgrid. You have that, so it has to have that And then the first the previous talk I talked about that primary control is nothing but your droop control will be there. It's a primary control because it is a directly responding immediate, the rate of change of deviation, the frequency response for that is there. Okay, whereas the secondary control is that one you are having that one is there. When primary control is not in a position to offset that deviations in the frequency and type over there. We are not going for that, for the type power part, we are not going for the primary control there, only frequency is there. Because this type pod is the indirect way of something like that power exchange between two areas or connected with the tie line. Even you can see about that the power exchange between the main grid and the microgrid, that as I said about that, there also means what can be made, based on that variation function of the deviations in the frequency there, how much power will be there, that can be made as a function of the deviation in the frequency, and it can come up for that there. That can be done for that. Okay, so here you have that. So another part is what that we have a that emergency for that, and for this one is there. This is a tertiary control for that. Means what that in most of the cases you will find out that that AGC and load frequency controls and other, that one is there. So that is mean for what small signal analysis. And you you may be knowing about that there is difference between small signal and large signal analysis. Why the differences one must know. One must know for the differences and others like that. So now the question is what you will find that for the some microgrid systems there, some analysis these are carried out, even that for the AGC and all this thing, with that even with the under the condition of some faults occurring in the system, some contingencies occurring in the system. So there also they want to find out that after that certain fault occurs, then come off for that. Now the question is how that is justified. Because if you consider that there is a sudden fault occurring in the system no longer remains in the small signal state. It remains, it swings into what large signal. Now the question is what, how is it justified? How the same model and working on the concept and parameters based on that and philosophy based on that, that are justified for that. One has to know for that. That is very important for this. Otherwise, simply nothing doing. Nothing doing. It works for that. May work depending on the certain conditions there. It works under certain conditions, like decoupling. Yes, it is possible under certain conditions. Your real power frequency and reactive power voltage, that the decouple, that's under certain conditions there. Okay, which may not be satisfying for everyone. Every case it may not be acceptable. Should not be used, because we do it for the research is a theoretical one. Nothing happens practically, so you are safe. You are safe, but the thing is, you implement that one for a simple system, it will collapse like anything, and you will have that face dismay, that horrible that. So that is what, like practicing engineers, they make mockery of that and something like, because we engineer professors never face with the real life situations and like that. We enjoy the without, of course, we never think of that. Means one has to understand that aspect for it. Otherwise, simply you cannot stand up there to face of that. Anyway, so here I was talking about that. You go for the demand control, that demand response and other things will be coming for that is there. You go for different type of critical load and other things that based on that. This additional part you have to come up for that is there. So that one will come for that. From here also will come up for that. This one, the under frequency load shedding. That is one part will be there. That is what there. It is specifically two parts important. One is what is the current frequency and what is the frequency. How the frequency drops, or variations of the frequency. It may be both ways. It's increasing or decreasing. So based on that, one has to go for that. This is not shedding. So if the shedding part will be there, then it has to be because the dropping of the frequency there. The rate of dropping based on the go for the more and more, all these things can be done. But as I said about that one is there, this logics and other all the things can be also made for this expert system and other things, much more. Anyway, that is there. But in addition to that one has to come up for that is that you have the demand response and go for that smart smart user, smart load, and smart consumers or something like that concept will come up with that. Then you have so we go for that is ultimately what switching on and off and all these things will be coming for that. That creates a situation for what some doing some analysis, and which is just assuming something and which is unrealistic. Unrealistic in the sense means what actual thing may be different for that when real life like it is there. But okay, that also of course one has to come up with some framework to evaluate that schemes, whatever schemes being proposed and other things. That is one part. Anyway, that is what I said about that is there. Okay, still 20 minutes more. So now I'll say about that. I have said something from now itself. I have already talked about this one. Some part of that one is there. Okay. Okay, this is what application I've taken from that VK board. There is about the IEEE fellow or something like. He has shown about that, that how that wind turbine that there you have to have that one. Then with that inverter, you go for that. How one has to go for that, that MPPD and all this. For the fuzzy logic controller, it is implemented for. And hardly you find so many, that part of an observation and other. There's so many inductors for the conductors. There's so many other methods people are asking for that is there. That is so simple for that. Simply that one is that this comes up for that is a much more realistic for that. Even if there is a variations of that also there. You have two part there. One is what for the speed of that is there. Then other one is what one can come. Not only there, even one more than that also one can come up with it, because fuzzy logic or expert system allows you that to introduce to consider number of parameters, keeping in mind that different operating conditions of the systems there, and under that one it will ask about what it will cost for that that controlling it. So what should the actions which has to be carried out for that? The wind velocity varies, how that so that one is there. Even as I said about that is there, one can come up with this also. Maybe what as I said, that this fuzzy logic also, that one, the controller also, that is also normally one that can be optimized using even meta heuristic algorithms. Been in this case also they have not used, just margin that without that from the journal paper they have got this good results without optimizing that one with meta heuristic algorithm. Suppose you same one work you one does it for meta heuristic algorithm, so definitely it will be performing better than that. Anyway, that is what I say about that. And these are the different directions of something like I have just taken from the same one. It is from the IEEE section. I just talked about that. On that one, the smart sensing. We talked about the smart sensing, metering, and communication infrastructure, where that intelligent techniques can be exploited for that. Is the same. Another one is for starting with that sensing, metering, because sensing also requires smart sensing. Okay, smart sensing, what is that? It is not only that sensing, that you have the information, the back and forth. No, it is not. That information itself is how to ensure the information is more smart, more intelligent, It is so smart is what it has to, how to make that sensing itself is more intelligent. Okay, I'll just say that I will discuss about that. Then again, metering is there. Again, they'll come up with that that communication infrastructure. So the metering also can be made so they come up with that. It should not be linear metering or stepwise or something like this. One can come up with it much more adaptive or other way like that is there, depending on this. Okay, and then communication infrastructure also. Oh, definitely, I'm not came out of the provisions for that, scopes for that modifications in the infrastructure for that, which maybe talked about that. That is the cognitive radio and all. Autonomous control and adaptive protection there, that also has to be for that is there, and autonomous control part is there for that. Then advanced data management and visualization. These are the areas where that these areas intelligent techniques can be exploited for that. It's not much, it's a limited way it is used for that, not more. Then one can think of the intelligent interfaces with the distributed sources and market. There's what interface that will offer the sources and market there. So for the market base, how that interface is made to happen there, and again that has to be what efficient, and that case is what, so that ultimate objective is what to exploit that one more and more distributed sources there, and in more efficient way, because you see, if we make use of the distributed sources, then our environment is already taken care of. It will be always what sustainable, that one is there, or environmentally what friendly, that one is there. But the thing is, you want to make it more efficient and effective. It's not efficient, it's effective, useful, fruitful. So when you go for that is a market. So market participation ensures for that the efficient use of that what is there. Then you come up with the decision support system for system operation and planning. Oh my God, this is the whole overall that higher level of that what is top of that system operation and planning for that there. That has to be made very adaptive also, depend the situations changing for that there. So we just look for that. What are the different things there? That I say about the sensing and everything else. Use the CTPDs. All CTPDs will be replaced with that one. No electromechanical. That one is there. So come up for that all optical based CTs and CVTs are that one is there. Come up with that. Not only that, use some other devices like ANN and some other one, so that like inequities or non-linearities in the responses of this one can be taken care of for that, or even any sort of noise and others can be taken care of for that. Again, that one is there. Here we talk about the RTUs node. Remote targeted is what that one is what using TPS. That one is there. This enhance the RTU signal function will be replaced by the high-speed PMUs will be there. We hope that one. Now the question is what is normally asked for that is there when the PMUs are in place, which gives us the phasor measurement of that, and the voltage always can be measured for that. The problem with us was how to get the phasor phases of that one is there, which was the outcome of the load flow study here. Why one should go for load flow study? Why one should go for load flow study? Okay, so that question is yes, load flow study is relevant. Suppose specifically under normal and the stressed conditions, so scenarios one can do that much more robust analysis of that one is there, the accurate analysis of that one is there, and that can be used for coming out with some inferences for the given situation, which may be something is better than nothing. That is what there. Of course, that current prevailing situation may be different than which was considered for coming out with that load flow results and others like that. Because we cannot of course there are nowadays recent efforts of that one is there, because once you have the PMUs are there and you do not have the state estimation and other things there. Of course nowadays another thing is coming up for that. If something goes wrong with the PMUs measurement there, then the state estimator may come for the help for that is there, and some recent way of that can be also used of that, so that like this can be supplemented with that. So normally what we will do is solve the network and the monitor the power quality and that power quality in some cases respond automatically to them. Rapidly the system support the kind of automated self-healing of this. Because this one, so because of the PMUs, and I know that PMUs are not many places are being used. So it has to be, one has to come up for that type of things, application of that. Why it is not much used? One more thing is what partially it can be done. So, but the thing is, that confidence of using this one, relying on this type of things, all these things, the expertise and skillness and all this thing of the operating personnel are lacking for that. There's not much available for that. So in that case, what day-to-day activities and others, like one things twice or thrice or 4 times before they reach out to that. Anyway, but when you go for that self-healing and fault tolerant self-healing systems are there in that one smart. This one will make that implementation of the self-healing and other type of features, smart features, and that one is possible for that there. But another one is of course for that the wide area measurement also is a network of this can provide real-time monitoring on a general national scale also. That is what also another the things are happening. One can come up with software which will create the situation, the generations for that. From dynamics, generation is what type of scenario means what the dynamical behavior of the system given the different responses disturbances in that one is there. That may also help that some of that the system for training that ANN or some other type of intelligent models there, so that it can predict about that this type of situation result into what maybe pointing to some sort of catastrophe or something like that. Okay, and then okay, so knowing this type of situations there on the wide area point of view that is there, one can predict that something untoward or unwanted things happening for that is there. So then what you go for that is what you can go for that autonomous control and therapy protection. That also is another part there, where the concept is given for that is what here the multi-agent based control system therapy protection there. So multi-agent based control system in that case means for different areas, small, large number of based decentralized controllers for normal. So you have the different small system together which are controllers which are mean for some part of the system there, and each will be treated for the independent of the other systems there, subsystems there. So every subsystem will be having a controller there which will be treated as one independent that one is there. So then you have suppose that type of how many controllers there together that one is there. So in a coordinated way, so that ultimately what that although the complex can be viewed as a collection of individual intelligent agents that adapt to events and surroundings. Okay, they will adapt to the local one. At the same time, they will think about that what are the interactions among that different agents are there, both competitively and cooperatively for the good of the entire system. There is one. So it is what decentralized, but what that integrated performance of the decentralized that control. We can say the controller. Controller is a different subsystems. Okay, so that adaptive protection also has to be, because when you have the smart grid, you never know the which way. It's a back and forth, bi-directional flow of powers, demand, and everything happens there. One just then, what happens to the protective relays will be there. So that has to be modified adaptively. It is not because the changes in the grid configuration, the everything it will be there. So how it has to be. So this is a real challenge for that. How to come up with that. As I said about that, if it is based on what the DC microgrid, that the things will be, these things will be very, that simplified way, simplified level, which can be easily, monitored, control, and other things. Philosophy also very easy to implement for that. So, so this one will be, so ultimately what you have to come up for that. Even that's in the protection also, that one can exploit that one. That protection also there, based on the given situations. So they, so under, because that the protective relays can be because they are meant for protective relays to be operational under certain conditions, there contingencies, specifically contingencies, which can be that emerging and are pre-evaluated for this one. So based on that means that depending on that point, as I said about that means by the fuzzy and neo fuzzy and all these things can be also exploited for that. So it's a very efficient area or promising area for that computational intelligence techniques to exploit here to come up with this one will be what is our adaptive protection system itself, a self-healing and fault tolerant and all these aspects. It can be better way to be implemented for this. Then advanced data management and visualization. Yes, this is a very important part of that machine learning techniques there. We come up with a huge data, PMUs and other like that, all that one is there. Everything is available in the digital form there. Once the digitization is there, so a digital form there, information is available for that. One can come up with so much, so one can exploit the data and then create different, that scenic, scenario generations of that, or even that same one there, digital, that one is there, can be made to, the playing that one situation will be there for the time, based that one situation happening for that is there. So it can be projected, and one can, even after that occurrence of the faults, after that even when things are happening, that also, that time also means what. So, but before that means one can come up with a lot of scenario generations through the use of the digital data, and then arranging the data in the different pattern, and then observing that through the visual perception for that as well. The visual feeling for that is there. So once it is developed for the visual inspection for that is there, which may help to come out with very expert inference, logical inferences for that is there. That is possible only one can come up with that. So one can say also that even because real-time visualization gives the operators a clear picture of the current operation status of the grid is there. Okay, so that is possible only what you have the digital, and then you come up with the different intelligent techniques are there which can be made use of that. So intelligent interfaces with the distributed sources of market is there. So this one has to be what much more, first and foremost one is what that one has to be able to predict that future demands. Okay, future demands, and then not only future demands, future even generation, possible probable generation, and then all the aspects will be there. So demands and generations are very much unpredictable at this thing there. Keeping in mind that one is there, so that that ultimately the market may be volatile. So depending on that means how to come up with that means predict that correct market prices. Even the market prices are supposed to be much more volatile as compared to the conventional one. We talk about day ahead market will be there, day ahead market. So that concept may not be also useful. That sense means what, that we have to be in a position to predict that day ahead or even 2 days ahead, 48 hours before that one occurrence of that, the correct that one load demand and the correct generation. Then only one can think of something like there is no market prices along, which requires a lot of intelligent tactics that is coming for that. That has to be. So even it is still today it is very much challenging. So one has to come up for that sense, like it's the deep learning and or other type of more competent, time series analysis, something like that. Okay. That is what that I say about that. Decision support systems for system operation and planning. So this is what that when we have that planning and all this thing there, you can come that operation, planning, and economics, dispatching, contingency analysis, restoration, blackouts are part of the smart brigade. Operation of smart brigade will be supported by a series of online such as what is there. This is what that means. What you have that that one cannot go the online means what? Yes, means what? Depending on the current situations for that is there. This situation the network must be. You have to have a algorithms which will point out that what may happen to the system under the different situation, the way it is increasing that parameter, it will lead to what, and this parameter going with it will lead to what. All these things should be what? So that intelligent algorithms which will be able to point out that what may be the ultimate, that risk factor of the current system being monitored for that, and it may come out with what, even draw the inferences also about that what should be the probable and effective actions, so that the future risk of that the failures and other that condition of the instability and all these things can be taken care of for that. So this is what. Okay. That is what that first diagnosis and prognosis are necessary. So this one is possible only for the expert system, which expert system or even with other type of an expert system, which is made that fine tuned with that materialistic algorithms and neural network and all this. That will make the diagnosis very faster and then give profit. Because the expert system will make the diagnosis very fast like this, and that one is there. You can come up with that for the training and so that when this is expert system together with hybridized with the neural network will make that given the situation very fast to come up for that. This algorithm, the neural network will be nothing but fuzzy neural is what the combination of what the rules are being embedded into the neural network, and then when these rules are what weights of the rules are optimized to your meta-heuristic algorithm, that make this one that for first diagnosis much more intelligent. Okay, that coming out with so many that other actions will be there, generating alarms, and even that showing up that all the the agencies and other operators will be sensitized about that what may be the cause of fault and other all these things. I think that's all.
Thank you, sir. Thank you, sir.
Okay.
As of now, we don't have any queries, but many of the students, many of the participants have expressed their views that it is a very informative session. So hopefully they will be learning a lot from that. They have expressed their views that it's an excellent session, very informative session like that. So thank you all. Sir has covered various aspects of smart and efficient management of energy systems, and hopefully all the participants will be benefited from this lecture session. So with this, we have come to the end of this lecture session. Thank you, sir, and thank you all the participants.
Okay, thank you.
We'll be meeting for the next lecture session.
Okay, thank you.